Good morning, everyone. Welcome to the third tutorial of Vision-Meets-Mapping. I'm the organizer, Sean, from Amazon. So first, let me introduce myself. My name is Sean Ma. I'm the Applied Computer Vision and AI Manager at Amazon. And below is my email address. Today, the tutorial covers various topics, including indoor and outdoor mapping, vision-based map making, vision-based high-definition map making, crowdsourced map making, semantic map, structure map, LiDAR-based localization, multi-sensor-based localization, 2D, 3D scene understanding, and location-based reasoning, 2D, 3D visual landmark detection, vision-based localization. We have a website of a tutorial, which is https://vision-meets-mapping.github.io. We will upload the recorded video to this website soon after we finish the tutorial. And also you could find out previous tutorials on Vision-Meets-Mapping on the same website. Today, we're fortunate to invite a few industry and academia leaders in the domain of mapping. The first speaker we invited is Olaf Booij, who's the manager of software engineering at TomTom. We have also invited Dr. Peter Kansinder, who's the research scientist manager at Facebook and also formerly known as Mapillary. We have Dr. Raquel Urtasun, who's a professor at University of Toronto and also CEO of Waabi. We have Dr. Ruisheng Wang, who's a professor at the University of Calgary and also director of the Geospatial Intelligence Lab. We have Dr. Ben Catlett, who's a manager at the Amazon Robotics AI. We also have Dr. Xiaofeng, who's the chief scientist at Amap or Alibaba. So today's agenda is a full day tutorial. Starts with an introduction from me, followed by a presentation from Olaf from TomTom, and then followed by Peter from Facebook. We'll have 1 hour morning lunch break between 12 p.m. and 1 p.m. Eastern time. And after that, we have invited talk from Dr. Raquel Urtasun from Waabi and U of Toronto. The topic is mapping for self-driving. We also have an invited talk from Dr. Ruisheng Wang at University of Calgary. Topic is mapping from LiDAR point clouds and images. We have an afternoon break, which is for 30 minutes between 3 p.m. and 3:30. After that, we have Dr. Ben Catlett, who's going to present on behalf of Amazon Robotics AI, followed by Dr. Xiaofeng from Amap Alibaba, who's going to present mapping and navigation in a hectic world. At 5:30 to 6, we're going to have a group Q&A from all the speakers, and then we'll wrap and make a conclusion for today's tutorial.
Very interesting that I was prompted to update Zoom when I started the link. I was like, oh no.
No, the same for me. So I have to restart my my Zoom again. So thanks very much, Olaf, and very fortunate to have you here. And then please kick off your presentation.
Yes, thanks. Let me share my screen. I'm not really Can you see it already?
Yeah, I can see it.
Okay, cool. If somebody, by the way, opens his camera view, then I do not feel all alone, but it's of course for you to decide to do so. Yeah, thanks first of all for inviting me, for inviting TomTom, and being able to speak here. Also, last time was really nice last year. Yeah, so first I want to say something about this presentation, because usually when you present kind of your work of the last year. And I will do a bit on that, but I thought as an industry partner, it is good also to really like shape kind of the research, right? So to not do the research, but ask the correct questions that should come from industry for the research community. So my focus of this presentation is actually that's also the type of what I hope to see in the next Vision-Meets-Mapping, Vision-Meets-Mapping 4 in 2022 already gives kind of I hope that this tutorial will continue for the coming years. So also for now, I don't know if anybody's there from the group. Mea culpa for not really putting your work here so big, right? I will mention a bit. So let's go for a small kind of a question. You can raise your hand behind your desk. Don't have to raise your hand in Zoom if you know the answer. So first question is here. Can you detect a sign in this image? Well, actually, now that I look, there's actually a sign here, but the answer is meant to be no. There's no sign in this image. Now let's change this a bit. So now what's the answer? Can you detect a sign in this image? Oh yes, there's clearly a sign, right? Let's change the bit again. Can you detect a sign in the image? No, you can't, right? There might be a sign behind this truck, but you don't know. So this is kind of, I hope it illustrates a bit for me the status of deep learning at the moment, what kind of tasks are being done with deep learning, and what is missing in the map making realm. For autonomous driving car, it's clear, right? It cannot detect a sign. But for map making, it's maybe different, right? Maybe you do want to check if the sign is there. So let me go on how I'm going to structure this talk. First, I'm going to give some TomTom background. I will not do too much advertisement because I'm not a salesman, so I'm not good at that anyways. And I'll probably say more lies even than a salesman would do. Then I will go into how I see what we currently are, how we are currently using deep learning for map making. And then already pose a question, right? Is this all that deep learning should do? Or could map mapping do more with deep learning? And therefore I'm gonna highlight two topics, and that's the sensor data pre-processing. I'm gonna go, and it's also a bit of my personal kind of interest project on a LiDAR, on a Kitty data set. I'm gonna show some results on that kind of makes the point clear that maybe you want some more deep learning there, research. And then I'm going into the second thing, like, okay, what do you do with this things that you have detected in image? I call it like feature post-processing, but maybe it should just be like map making. And then a small recap. But first, something on TomTom. So TomTom delivers location services as a whole, right? Also about traffic and these kind of things. But in this talk, it's just about services for road vehicles. So vehicles that are on the road and need to have kind of, sometimes it's seen like a fifth sensor, I don't know, another sensor, which is just like this service, the information that it gets, maybe from the cloud, maybe from a map that's already uploaded. And for example, it's driving here, and through the camera it sees this, right? Maybe there's a sign behind this, watch out for kangaroos, but it cannot see this, right? So should it watch out for kangaroos? Well, we then provide the service, yes, you should watch out for kangaroos. There's a sign there that you cannot see because it's blocked. And so how is this done? I think this is quite common to a lot of map makers. You just have a lot of data, and this data you take yourself. So you camera, you have cars driving around with cameras, lidars. They have GNSS systems, IMUs. You also maybe buy some satellite data, and then you maybe also have all kinds of other sources. In TomTom, this is kind of a big thing, right? TomTom is in this area for quite some time, and that's also this picture I drew here in the bottom. Some more about that. So, but the idea is, right, what's the challenge now? It's gathering all this data and providing the service, so keeping your service up to date with the latest and the best information there is, the data you could get. So on this picture there below, so this is a nice graphic, but let's speed it up. So this is Amsterdam actually, and we get a lot of data from this. And it's so, you see, right, it's not as images, it's just location data, right? It's just the devices that TomTom has everywhere and these kind of things. We know where they are, common to some other companies. And this is the information that that could be used to create the services. I work in Amsterdam, but I should say during COVID, I worked in Amsterdam because I didn't work there for a year now. Sniff. And when I was working in Amsterdam, it kind of looked like this. So a bit about maybe the group I'm working in and myself. We have a group in Amsterdam of like 25 people, focused purely on using machine learning to get the most out of our data. It's not the only group in TomTom doing that. And here you can see that we actually usually work close to each other. And we're in a bigger group unit called autonomous driving. It's called autonomous driving, but it's also services for driver assistance systems. And we have research. We do research in the group itself, but we also collaborate with. I see participants can now see your screen. I hope they could see it already. We also have collaborations with universities. We already collaborated quite a bit in the last years, but we also now instantiate this Atlas Lab. This is now running for more than a half year. There's already 5 PhDs started. 1 PhD will start soon. And we're also collaborating a lot with the TU Delft, Technical University in Delft, in the efficient deep learning realm. That's like a project there. And with that, we also have 2 PhDs who are working there for quite some time, but I will not expose their work, right? It's, I think, something that universities can do much better than me. So let's now go on to the current status of how deep learning is mostly used in map making. Of course, I won't say that this is like everything that's done with deep learning, because probably there's much more. But just kind of like where the focus is now on deep learning. And if you look in map making, so what is the part that actually makes which really made the most benefit of deep learning? Well, that's actually these kind of things, right? So you have an image, and you're gonna detect here in the image the sign, and you're gonna categorize it, what the sign is. So for example, there, watch out for kangaroos, and even the subplate, right, next 10 kilometers. So first, this kind of task 20 years ago, or even 10 years ago, was very difficult, right, to do these kind of things. I mean, you could do it, but it's now you can do this probably like within a few days. If you start from scratch, back then it was more like a PhD thesis. And so this is clearly kind of more or less copy of what is being done outside of mapping, just in deep learning, right? It's just a detection of things. So I think it's great that all the mapping companies made, like also us, TomTom, so quick use of like this field, this emerging deep learning field, and just started using it straight away, and actually feeding back also to the deep learning community, and we're really working together. Of course, this is also a bit because of the autonomous driving hype that this was possible. But of course, this is not. I also do not say, okay, this is the benefit. This is all finished, right? There's a lot of things that's not finished in this kind of part of, for example, detection of signs. One of the things that is kind of a bit troublesome and which really requires still some work is kind of the gap between what is done in research and how it's approached with the challenges that are there, and actually the stuff that you need to do in industry. So the data sets usually used in scientific world, like COCO or ImageNet or whatever, they are really good, but still there's differences. One of the things is that, well, in these data sets, there's also this long tail distribution, right, of rare classes or objects that are sometimes not seen that good, right? But that only happens very irregularly. So for example, glasses, right? Usually they're on a face. Sometimes they're not on a face. But in like the real world, this is happening even more, right? So that's why it's even longer tail. Other thing is kind of the different annotation quality. I did not see this mentioned many times. Usually in industry, you annotate not only to create a data set for learning a system, but you also create a data set to figure out maybe what the customer wants or what you need to detect. And in this way, you probably do not have kind of the same quality. Some things might be much better. Sometimes some things might not be so good. Some things that might be much better is, for example, the amount of different classes. You would just add them, right? And if you make a data set for science, you probably like stick to a confined set. But for example, really cropping them nicely, in industry doesn't really matter sometimes, right? And in science, it's usually the purpose to make kind of this kind of things perfect. Other thing is the ambiguous classes. So there's a lot of classes that are actually, it's like unclear what it is. So here I already put, so for example, this sign, this stop sign, which is in the back of the truck, you could argue that it's not a stop sign because it's not like a static sign on the side of the road. Is it a different class? Yeah, I don't know. Subplates is also kind of a thing that's really like, sometimes really ambiguous. Is it kind of a plate, yes or no? Is the sign yes or no? And we are also working on this. So one of the things we did was, especially for this kind of thing where you have like a lot of classes, and some classes are very rare. You could use taxonomies, because in a taxonomy, so some things are maybe a bit unclear what it is like specific, but you do know it's kind of general category. And that's also captured in these taxonomies, like WordNet. This is something we also use to kind of to make our classification system better. Also, for example, you could say you can have the category, but then not the specific what it is specifically. So you know it's a motor vehicle, but not a car, a motorbike, or truck. Then annotation becomes cheaper. These kind of systems exist already, but for detection architectures, especially modern detection architectures, they were not really working because most of the systems worked with softmax activation function. So what we did is we made it work on. Oh, that's maybe the next slide. So first, I should say, like, okay, so how you can benefit from this, how you can learn your system, is to not just have a loss on the specific thing, but also a loss on the categorical type. And to do this, you somehow have to fuse the activations of the different specific things into the categorical activation. You kind of have to compute this activation because it doesn't come from the detection network itself. And then you can just put a loss on that like fused activation value. And then you can have like different losses and you can kind of weight them while training and use them both or multiple if you have a lot of levels in your tree. And the thing is now that with softmax, it's kind of easy to sum this up because they're all unique, right? And they sum up to 1. So the probability of, for example, here C1 and C2 is just C1 plus C2. For sigmoid, that's not the case. And that's, for example, used in RetinaNet. There you cannot just sum them up, but you somehow have to take a union of them. And that's what we do in this paper. So if you want to know more about this paper and the results, just go ahead and look at the web. Like I said, I'm not going to go in depth to all the work. Another work we did, which is more on the label, the annotation quality, and mostly like the amount of annotations you have, is the work by David Biertempel. Prior to segment foreground cues for weakly annotated classes in partially supervised instance segmentation. So this is really like the task that we approach here is, so you have maybe a lot of detections, but they're all expressed in boxes. And you want to use those to increase your instance segmentation, because for instance segmentation, maybe you do not have that many data, that many annotations. And there has been work on this, but they suffer a bit because they usually they detect what is kind of the if you have a box, what is the object in this box, and then they use that as kind of a start for where you do your where you start your segmentation. And as you see here, for example, on the top, there's a shoe and a cat, and the shoe is something that is seen as the foreground. So that is the one that has the activation map. Well, actually, the cat is where we're interested in. But because the class is not used here in these systems, you cannot use that correctly. So how this is done is to kind of fuse or kind of do these kind of things in parallel, the classification and the mask prediction. And you, when you do the classification, so that's here the green box at the top. You compute the class and the region, the box, but you also compute the class activation maps from the weights in the classifier, and you use those as a prior where to look for the object and the mask. And the interesting thing is actually, but it's kind of more like a bonus, that this class activation maps, they are as they were already like differentiable. So actually the mask output, the mask loss, can also be used to update the class activation maps, and thus the weights that are used for the classifier. And this is needed and handy because then the classifier will not just look at the most discriminative part, but to kind of more the whole kind of object, or a bit bigger, so it's easier for your mask prediction for your instance segmentation. So very similar, well, not very similar work, I should not say this. A related work that's done by Erik Stammes. Find it if you can, end-to-end adversarial erasing for weakly supervised semantic segmentation. So here the task is a bit similar, that's what I want to say. But it's not using object detection. So it's not like this previous was on mostly tested on the COCO dataset. This is a Pascal VOC image, I think. The idea is here that you use the image class itself to as a weak hint on where to look for the for the segmentation. And it's not just one object, could be multiple objects, right? And the idea is here not to use, oh, I see, didn't fit completely here. The idea here is that you kind of erase you want to erase that part of the image such that you cannot detect the object anymore. And this is quite a common thing. People usually use something where they have like 2 separate steps or multiple separate steps, where they first try to detect the object. They compute what was attended to, for example, if class activation maps, and they remove those parts, and then they again run a classifier to detect what is there, and it can only use those parts that are still visible and not masked out. And so common way is to do this iteratively, and then all the parts that are blanked out in the end, you sum them up and you have your segmentation. This is a bit not nice. Usually you have to separate, right? Because you're solving kind of different problems maybe. Well, it's actually one problem. So Eric did something where you actually have just one pipeline, and you have you have a CNN that detects where the image is and its loss is class, and you then train this also with an adversarial neural network that tries to get the class in one go. So this is how it works. On the left, you see this image of the cat and the dog. So there's different classes, a cat and a dog, right? So there's different attention maps. This localizer is trained with the classification error. It creates some masks based on the classification maps or attention maps. These are then used to blank out the image. And then there's an adversarial network that does the same, right? Tries to classify, but if it succeeds, it is used as an adversarial loss for the localizer that needs to localize the whole object. And the key here is, of course, that this mask you should backpropagate through the mask. So the mask is made in a way that it's differentiable. So these are kind of the things that are kind of building on top of the existing deep learning trend, I think. And they're very useful, not only for us at TomTom for map making, but they're also useful, I think, in general. So you also saw here, most of the images used are actually, data set used are just general deep learning data sets. They're in general handy for all kinds of tasks that you want to do, all kinds of industries. But so the question is, what about the rest of map making, right? Because this is just the detection part and the classification part and segmentation part. And well, if you look a bit at it, so there's not much deep learning happening there, not much learning in general. Mostly it's like handcrafted processes. The maps that are created are usually designed or in collaboration with customers designed to have certain entities in there. And the updating of this map is also usually not in a learned fashion, right? It's usually done by some handcrafted, some might call it even ad hoc solutions. And I think this is somewhere where we should really change in map making, because if you look at what deep learning is about representation learning and end-to-end optimization. Well, that's two of the key kind of things that deep learning give. And what do we want? We want to have representations. That is what a map is, right? Representation of the world. That's handy for example, autonomous driving. And actually what you want to actually have this complete processing of your source data to this map end to end. And end-to-end learning, that's also really something that's deep learning strength. So let me go a bit into this sensor data processing and also a bit into my hobby project. So data processing is very data pre-processing. Sorry, it's very convenient. It's very nice that a lot of pre-processing is being done. and then I'm thinking mostly of the data sets that we use in deep learning. So you can think of, for example, if you have panorama images, so you have a car with different cameras, it's actually handy to stitch them together and to have full panoramas, because then you just have one image. But of course, there's also then like a seam where it's stitched, so it's not really end to end. You can also think of GPS and IMU. That's used a lot in mapping, but usually they're just fused using standard comma filters or other filtering techniques, and they're not even fed into the deep learning system. They're just more like seen as, okay, this is your ground truth location. I'm exaggerating a bit here, right? I know that there are works that do this, but just in general, right? The focus is not on those parts yet. And yeah, then my pet project, leader data, that's usually seen as sparse unordered point clouds. It's, well, leader doesn't really get this unordered point clouds, right? But that's how we see it. That's how it's pre-processed. Yeah, so my what I want to suggest here is that actually when you do this, you actually hide some data, and at the same time it's suboptimal, which is a bit extra, right? So you're maybe making it more difficult even if you're not hiding data. So now in this leader data, it's commonly seen as like sparse unordered sets of 3D points, and this inspires a lot of people to use things like graph networks, or well, networks that are invariant to position in the invariant to order, which I think is great, by the way, and I think it's because some of these things are already there, and also it gives great insight. But actually, if you, oh yeah, so later I'm gonna say why I think that's the wrong way. But still, also, if you look at how leader data now, for example, the Kitty data set, but also other data sets out there are being used, a lot of times they're actually projected again to the panoramic view per scan of the leader. And well, here you see in the top like a common way that people do this. Although I did this myself, I hope it's kind of similar to what you see in papers. And you can see all kinds of problems in this, right? So in the bottom you see this this car on the left view. It has some interesting things. So you can see there's kind of some pixels are just black. Yeah, that's just because at that point there was no LiDAR measurement. You can also see this motion shadow, this black in the front. That's because of the motion correction that was applied. And the car was actually, because of the projection, you cannot see behind. So when the LiDAR was seeing this, it actually could not see this kind of place where it is black. That's why it's black. On the other side, you can't see, but on the other side, the other thing is occurring, right? The car actually is blocking a view, what the LiDAR could see, but because the car then drove there, it's blocking that. And there's also some points here missing here and there, because there's sometimes like 2 points and they do not fit in 1 pixel. All in all, in this image, I computed 12% of the points missing. Of course, you can make the resolution higher and you will get more blank pixels. But still, this projection, that's really kind of something that works. We also had a paper on this last year, and what you usually see, and that's, so we were like, for a small moment we were the Semantic Kitty top runner, but quite quickly others took that position. But if you look at what is there out there, all these things in the Semantic Kitty challenge, probably also in other challenges that are kind of similar, they always use this kind of range images. They usually use like range images in combination with something that does something with the points themselves, so in 3D, like we did, right? It was just like a non-standard UNet kind of network, and then kpconf which then give a class to every point, also the points that were blanked out in the during the projection. But now when we look at LiDAR sensors itself, so this is this Velodyne 64 that is quite commonly used. How do they take their measurements actually, if we're talking end to end? So they are actually really making some so in this one they make 2 beams at the same time, and they just make these beams in set times, 2 beams, 2 beams, 2 beams, and then they of your scene, right? So you could see this like this, right? They do not do it in one row, but they do it kind of spread out over some 20 by 20 degrees or 20 by 40 degrees range, so like a small image, and they kind of do these measurements like this, and then after a while they have kind of so say this one has like what is it, 9 one is probably outside of the image, 10 LiDAR probes, 10 LiDAR measurements, and it does this while it's rotating, and after the next like nanosecond or something, it takes another shot, and it keeps on continuing and gets this nicely covered measurements. It kind of resembles an image more or less, but it is kind of a bit non-linear, and it's actually sparser, right? The pixels do not really overlap, but as you can see, it's quite ordered. It's not the case that this is an unordered point cloud. Also, there are some gaps in there because some LiDAR measurements do not return anything, because they got reflected away or whatever, or they were hit on the sky and then you also cannot see them. So what I did here, I actually reverted this laser probe calibration in some Kitty scan, and then you just have all the measurements of the LiDAR, and then but they're kind of like not in the same direction, so I had to shift them again discretely, and you kind of get this image, and it resembles a bit this RangeNet, but actually it's quite different. One thing is, well, here I named it all of them. So the result of the left is just a projection back, and the result on the right is actually undoing the LiDAR probe calibration. So LiDAR probes are the different lasers of the Velodyne. And you can actually see that, so every pixel here is actually a measurement. So all measurements are here, and each pixel is a measurement. This is different than this, right? Another thing is like these motion artifacts, they are gone, because these motion artifacts just came with the getting the motion away. Other thing is the kind that's something I saw later. So this is on the left and the right. You can see this awkward kind of squares in the lower image, which are not in the top. Well, actually, in the top, it's kind of doing something that's kind of erroneous, because the LiDAR is turning around, but it's not like a circle, right? Because the car is moving, so it's more like a spiral. So that kind of here is assumed to overlap, but it's actually not, right? It's not overlapping. And in the bottom, I did not do this overlap, because actually it is taken at a different time when the car was further away. Also, maybe, so this is about, so yeah, I'm just saying, like, see, you can do things, and probably this is more, you can also just use this, and you do not really need this pre-processing. The raw data is probably maybe better even, because you do not have these artifacts. But there's also some other thing which is nice, which I saw already some time ago in other data, but here it's also apparent. So on the left is again the image taken with the just projecting back the LiDAR data. You can see a lot of gaps in there. That's just because of discretization problems where some pixels do not have any points. On the right, there's also things missing, but those are all the measurements. So actually those measurements did not return. And then if you look where those measurements came, it was in the paint mostly, right? So some things on the top here, it's not paint. Actually, probably when you shoot a ray at the paint, maybe sometimes it's kind of bounces off and does not come back to the center. Maybe somebody knows what's happening here and he can tell later during the questions. But what I want to show here is that you can see there's actually information in there. And the pre-processing maybe hides this information, because maybe it's handy to know the paint. So that comes to the conclusion for this part. I think it would be good if we look more into this direction. What can we do? So can we create deep learning models that directly use this raw sensor data and not need these pre-processing steps? But maybe you can also do something else and just do this pre-processing, but not do it in a handcrafted manner like we do now, but do it actually in a learned manner, and just couple this with your next steps, your classification and your detection. So let's go on now. So that's kind of before we do this feature extraction, right? And then we do this feature extraction, and that's kind of there we're good at using deep learning. But then afterwards, what do we do? So I called here feature post-processing. That's silly. So you detect a sign and you just put it on your map, right? Given your GNSS or IMU filtered data. Yeah, that's a way to create some map, and it's probably useful also for people like us. But is that actually the way to do it? So what if there was already a sign detected from a previous source and it's already in the map? It's a slightly different location, of course, because of measurement noise. Yeah, you can of course do some thresholding here, right? If it's close by, then you are not using it, or you're gonna just wait a week and then cluster all your results. But then if it's slightly different, if the sign is detected as something else, so maybe it was a different sign, maybe it was a detection error, and it just saw a different sign. Yeah, so maybe you can just wait until you get 10 the same signs and then say, okay, now I know what it is. And say you have a sign in the map and you had a sign here of watch out for kangaroos, and then there's no sign. You cannot see the sign in this image. So what would you do then? Would you just remove it? You could do that, but maybe you did not see the sign here, right? Maybe you would want to do something different then. Or maybe you slightly see the sign, right? Just on the top. So it's not enough in evidence to know what the sign is, but it might give some confirmation if you already have it in the map. And you can, so this is like a truck blocking, right? You could say, okay, I make like use of the truck detector and say if the truck is in front, or you can estimate its depth or something somehow, then you know. But maybe it was just a lens flare that was made it difficult for the detector. You can really go wild here of all the kind of things that could go wrong. And the question then is, do you really want to do this using handcrafted things, or you want to do some learning here? And I think that's kind of the thing we should do, right? We should really invest in how do you learn to map, or maybe how do you learn to update a map. I see learn to map actually as also maintaining a map, keeping a map alive. And how should we represent the map that allows this, allows to update it? If you first see a sign that has this lens flare over it, how can you kind of give a trace somewhere in your representation that the next time you get something, you can kind of update this or use it or like dismiss it or confirm it or these kind of things. And well, what you can see then with map update, you have this kind of, probably you're going to look into something that kind of goes round, right? Because you have to make use of the data of your past, and that's already in representation. You get some new things. How are you going to use that? You don't want to just keep all the things in the past, right? You don't want to backpropagate there. So you want to keep this in representation. You want to get a map get some new things, and update the map. So it's kind of this loopy behavior. And that's kind of difficult, right? Because it kind of breaks the paradigm in deep learning of doing things feed forward, where you get data in and you get detection out. Yeah, you could think of reinforcement learning or these kind of things, but I really think this is an open question we need to answer. And yeah, so one of the things I was thinking personally is that you could maybe see this map that we're creating, this representation, something that should be able to predict new measurements. And in that way, you could see how well it is able to predict new measurements. If you get a new measurement in, the likelihood should not be 0, it should be something. And yeah, that's why I also put this work in, which we already did in 2020, which kind of relates to that. So that's why I thought it was good mentioning it here. Because here we did scene flow estimation. So that's the task that you get usually two, well, in this case, really two scans of a leader, for example, from a kitty, but you could also think of 2 depth maps from a depth map camera. And you want to predict the speed of the things you saw in your first or second image or data. It's not just like looking for the nearest neighbor points, because you really want to know what is the speed of that object on which this point was lying. So you need to make a representation there of the world. And there, how we solved this was during self-supervised learning. So you get your 2 point clouds, you hide some of it of the second point cloud, and then you try to make a representation. If it is good enough and it knows your scene, it should be able to predict what your those missing points should be. So this is kind of in line with what I suggested, right? You have a representation that allows for prediction. So to recap, I think we should work, and I hope to see work on, well, more focus on the following research questions. That's how to learn to map, of how to learn to update the map, how to learn what we should represent to allow this. And then on the other side, can we create deep learning models that directly use raw sensor data, like IMU, like LIDAR? And can this pre-processing be learned end to end? And I think this is how we should do this is deep learning, right? So mapping needs representation to learn end to end. Mapping needs more deep learning. And I already put this some time ago, so it's not now, but I realized when making the slides that I'm the first speaker. So maybe this is not for the next Vision Meets Mapping, but maybe it's in the coming hour, some of the speakers will already answer some of these questions. That would be great. And that ends my presentation. Thank you for listening. I hope it wasn't too hard. Coping with my slides. And if there's questions or remarks, I'm open.
Thank you very much, Olaf, for your presentation. And now let's open up this question. And I don't know if you can unmute yourself, but if you need my help, you can also send me a message. But if you can unmute yourself, feel free to start asking questions. Thank you. I mean, from the audience.
I'm also very open for like naughty questions about TomTom or whatever, right? Doesn't have to be related to the slides.
I see there's a question online from William asking the self-supervised paper. Did your model work well without further supervised training?
So there we did. It's so usually all those methods there use kind of a bit of a mix. And I think for us also, if I remember, it was last year. I should know, but I don't anymore. I don't remember if we really specifically had runs where we did not use any supervised training, but I think I should be on the safe side, and I think we did some supervised training, but then not on all the data. But also I should say that a lot of this work in this realm is being done on more like artificially generated data and not on, for example, point clouds coming from lidars that are on autonomous cars. I hope that answered the question.
Thank you. Any other questions from the audience? You can feel free to unmute yourself.
Usually when I say I work for TomTom, people ask, oh, aren't they going to be bought by some other company?
Oh, we do have another question from online. Marco is asking, how large do you think is the gap between this artificial generated data and the real data?
For this, in this self-supervised data, I think the gap is very large. And I think this is also because of not knowing much actually maybe it ties in a bit with my thing about how to look at, for example, lidar data. Doing things with point clouds, using, for example, neural networks that things like point net derivatives, they're difficult to use than in, for example, an adversarial training setup. I think this artificial data sets there, it's usually quite different than usually they use like depth camera kind of setups where you really have a nicely you really have a nice scene with like things flying through there, and you really have one pixel is one measurement. In lidar, if you just look at that points, it's really sparse, and then it's really difficult. Also in Kitty, if you look, for example, but I think it's in general for all autonomous driving data sets, a lot of the points are, for example, on the road, and really a lot. Usually with this artificial generated data sets, you really focus on the things that are moving, while in autonomous driving data sets, mostly nothing is moving. And most of the things are very flat. So if you are going to use like general solutions, then you're not specifically coping this, or the neural network is not allowed to cope with this, you probably get into these degenerate solutions where you focus too much on this, for example, the road, which is a plane, so it's moving relative to your lidar, but the lidar just sees the same plane and it measured it at the same place, so it seems to be static while you're moving 100 kilometers per hour or 60 miles per hour if you're in New York. I hope that answered the question.
Okay, any other questions from the audience? Yeah, feel free to unmute yourself and ask questions. I do have a question, Olaf. So you didn't mention that here, but you mentioned part of in your presentation. It seems like the technology is what we're developing is using deep learning, and definitely save a lot of like human effort, and especially you're saying in the future map making or any other post-processing or pre-processing step could also be end-to-end learning. You know, one thing we didn't talk about is the quality of the data and the scalability of the approach. So, you know, I understand TomTom is a global company and have a lot of like data sources from around the world, but those data sources might have different quality. And what's your view of this, you know, scalability versus the number of data? For example, you could have very high quality data at certain area, but with very small observation. You might have like one pass of the road, and other places you might have thousands of low quality data. And then you also mentioned that you have 10 observations, and you might want to update the data. So what's TomTom's view of this global coverage as well as the quality of data control?
Yeah, so I think one of the things that TomTom is doing is being pragmatic about this. Of course, it's great to have something that like a system that fits everything. Is very generic, but in the end that doesn't work out. So you should also know that it's not just all the sensor data. It's also just data about from governments. Like they decide to all of a sudden change the driving speed because of climate change measures or safety, and this should also be incorporated. And there's also kind of quality concerns there, right? They say that they're gonna rebuild the highway, and then they delay it for a month without saying this. So this pragmatic view is kind of what TomTom is doing. So if you have specific knowledge, you do need to have specific knowledge for each source of data, and you should treat also the quality of that source of data. And it's very good to not have a centralized system with one group knowing about all these qualities, because that's just too much. That wouldn't be efficient. That's maybe more like a global kind of answer. Like I think TomTom is doing this. More specifically, I think how this kind of things should be tackled, and how TomTom is partly also doing, is to put the quality in the map. So in the representations already have the notion of quality in there. So you're not just gonna harvest data and just dismiss low quality or something. No, you're gonna get in these low quality sources and somehow get this in your representations, that something might have changed or something, or there might be a sign, but with a low chance. And maybe you just keep it inside. Maybe you expose it after getting through some threshold, or maybe you always expose it. And that's kind of TomTom usually has a lot of bilateral kind of interactions with companies. So for each company, that would also be different, what they would want, right? Do you also want the low quality or just the high ones?
Okay, thank you. Any other questions from the audience? Okay, I have another question I could ask.
Yeah, okay.
I've been working on this. So another question you mentioned, right? So there could be multiple observations of the same sign when you're passing it, and then you need to make a judgment on when to update that sign. It could be both cases where you see multiple times you see the sign, or multiple times you don't see the sign. So it seems like that there need to be a balance between the speed of the updating versus you trust the source or not, right? The same thing, like you want to fast update, maybe you don't need to wait for 10, but then if you do want to make sure you're sure it's right, then you have to wait until 10 observations. But you cannot control the car, so maybe the car passed there already, being delayed. So is there any sort of a good answer? I know this is almost like a secret from the company perspective, but can you share some of the thoughts on this, or maybe inspire researchers and to look into this? And because I think this is a problem for any mapping company, right? So even let's say we have large scale kind of a data, we still need to figure out the balance between updating speed versus the quality of the map.
Yeah. So I do not expose much secrets if I say, right now it's kind of like a mix, right? Sometimes you you have some delay in your throughput so that you have like a buffer. And in some cases, you just have some quality kind of things in there in your representations, at which you already even expose to customers. And this is there's a mix there. What I really hope that this will be one of the largest kind of things that people will invest their time in if they're interested in map making. Especially this question, right? How do you represent the uncertainty there? And not having no evidence, that's kind of the thing, right? It's kind of interesting because I've got confronted, I don't know if this is like in general the case, with some people reaching out back to Dempster-Shafer theory and these kind of things. I don't know if you know this kind of thing, like possibility theory, to have a richer kind of way to express your uncertainty about things. I don't know the solution there. For me, that's more like hearing those kind of sounds makes me think, okay, there's quite some things we still need to discover. I hope actually it will be more on the probabilistic side, that you always have like a nice belief state of representation. And the belief could be multimodal, right? It could be, okay, they refurbish the whole street or not. And so if you see that they remove 2 signs, you don't have any evidence of the first signs, your belief is, okay, it might be that is deleted or not. And this kind of multimodal kind of representations, I think that's kind of the area where we should look into, using then the fact that if your model is good, so you can measure that, because then it should be able to predict the future. And it's multimodal prediction. It's kind of difficult, right? Because it's not, you should not just take the average of your belief. You should do something different. So maybe there's a space also there for things like adversarial learning, where you know that your belief, you can guide samples out of there, which are could be real, right? And still are kind of, you have a lot of evidence for them from your data. Yeah, very vague. So I think enough material for a lot of PhD projects.
Yep, sounds good. And then there's one more question from the audience, from Alao Taibi. Sorry if I'm pronouncing your name right, but they were asking, how do you define low versus high quality data if you have a lot of data?
Yeah, that's a good question. So sometimes you just see that, sometimes just the content itself, right? It is, you only have 3 types of signs or 3 types of colors, and you know, okay, it's really discretized a lot. So there's a lot of discretization noise, you could say. But sometimes you can just see it's inconsistent with what you know or with the data stream itself. That's how you can measure quality, right? Another thing is, of course, the date, right? When things are really outdated. But that's another axis. There's a lot of kind of different things you can say, I think, about quality.
Okay, we have another question. That's great. Harish was asking, what's your opinion about dense map, like full 3D map versus feature map in long-term mapping point of view?
Yeah, good question.
Sorry, long-term mapping point of view.
Yeah, so I think so it's, for me, I think you should look at it like this. A map is a representation or a model of the world. It should be such that it's useful for predictions that are useful. So that 3 leaves fall in the winter. Okay, maybe that's something you want in the model, but there might be things in the model, right? Is the person next to the sidewalk sad or happy? Maybe that's not handy to have in your model. But other things are handy, like how high is the curb or something. But the other thing is that in the model, there should be something that allows it to update, right? So that's, for example, you have to have your uncertainty should be rich enough to allow it for updates. So if you do not see a sign one time, you should not remove it or just keep it. No, you should kind of put a hint there, like, hey, I didn't see it one time or something, and just count the number of times that you see it. Could be such a simple thing. If you then look at the question, so 3D maps, yeah, if you just have a 3D map without this kind of possibility of this multimodalness, so that there might be multiple truths, then it wouldn't be very handy. And because it's also very expensive to maintain, I think it's not handy to do that. Also, it is probably way too much for your customers, right? You could maybe tell if somebody's happy or sad using the 3D model. So it's better to be closer to probably what you actually want to predict. Another thing is I forgot it. Oh yeah, the thing, if it should be locally or globally correct. If you have a really 3D model, probably you're also thinking more about globally correct, and that's usually not that needed if you're driving in a car. You do not really need to know in which city you are, maybe even to drive safely. So that's maybe also handier with a more like topologically able map.
Okay, thank you. We have another question from RSK. So that's good. We have a lot of questions. So they were asking, how do you handle areas like under construction where lanes are added or medians are constructed?
Yeah, so of course they are the most interesting, maybe, especially on highways. These kind of things can take a long time. And the interesting thing is also that sometimes they, especially in the US, I saw this, that they built them back after a year in exactly the same way with the paint at exactly the same space. So you would wonder, should you throw it away what you had or not? So you should also think about, so what do most customers do if they have like highly like autonomous driving features or highly automated driving systems? They probably switch off their systems if they come in such an area. So as our customers concerned, usually they probably just want to know that these kind of things are happening. But from a mapping perspective, it's very good, right? You really should have a look. You should really know that these things are there. Also, just to monitor when they were finished and when they started. Also, the problem is sometimes you cannot go there yourself when there's under construction. That's also kind of interesting.
Okay, it seems like from the mapping perspective, we just want to know the beginning and ending of construction, and then after construction, we'll update the map, right? But in the middle, probably not updating map because it's still in construction.
Yeah, you have to monitor it, but it's not that useful for your customers usually because they are usually on the safe side, I think.
Yep, sounds good. Thank you very much, Olaf. I think we're out of time, but thank you very much for your presentation and also your Q&A. We'll kick off the next presentation, and I think our speaker is here already, Peter Consider. And Peter, do you want me to play the video on my side?
Yeah, I think we can just play the video. I'm gonna stay here and be available for questions. And thanks for the invitation.
Yep, sure. Sure, I'll just start playing.
And I'm a research scientist manager at Facebook Reality Labs, supporting a team of researchers in Zurich, Switzerland. My team was responsible for basic computer vision and machine learning research at Mapillary before we all joined Facebook last year. And I'm grateful for the opportunity to talk again at this tutorial. Today, I will present our new dataset coined Mapillary Metropolis, a city-scale framework for multitask benchmarking of semantic 3D mapmaking. Building this dataset was, and still is, a massive challenge, and has been addressed by the set of talented people listed on this slide. I want to thank everyone for their ideas and contributions that eventually brought this dataset to life. So why do we need yet another dataset? Our main goal is to fundamentally rethink CV and ML benchmarking for 3D semantic mapmaking. This means, instead of following a conventional task-specific approach of testing algorithms in isolations, we wanted to generate a 360-degree benchmarking playground for mapmaking alone. This will enable both accurate assessment of given mapmaking pipelines, but also help us to systematically study which map building components require more research. The basic idea of our dataset is to collect many different, heterogeneous, and complementary data sources as shown on this slide, and to align them all within a unified reference coordinate system where we can interrelate data from different modalities. This is in stark contrast with existing approaches, including some of our own previous attempts, where we have built datasets for assessing specific problems like panoptic segmentation, depth estimation, or traffic sign recognition. With the Mapillary Metropolis dataset, we have built a full-stack city-scale benchmarking platform for 3D semantic mapmaking. Looking at the mapping pipeline sketched on the left, we want to move closer towards an end-to-end assessment of map building rather than assessing individual blocks at a time, which is the predominant approach at the moment. Our hope is that, given all the modalities listed in the center of this slide, from area LiDAR all the way down to survey-grade ground control points, to build the foundations for next-level mapmaking, where we can address many of the tasks shown on the right-hand side, ultimately leading to improved map building results. Here is an overview of what I will be talking about today. Having started with our motivation, I will dive deeper into the 3D data generation and alignment tasks we've pursued for our dataset. The second part addresses the current dataset extent and discusses the type of annotations we're making. Finally, I show some preliminary task definitions, corresponding results, and how we anticipate benchmarking in Metropolis. Let's start with describing our 3D data generation pipeline and how we address the problem of data alignment across multiple modalities. We leverage on high quality and high resolution panoramic image data captured and provided by the City of Detroit and made publicly available at the Mapillary platform. We address the problem of accurate geopositioning by leveraging ground control point information, which we propagate through all data modalities, including street-level LiDAR, aerial imagery, aerial LiDAR, and CAD model data. Ultimately, we want all of these modalities to be aligned and accessible for cross-modal learning. Our image-based reconstruction pipeline builds on a modified structure from motion multi-view stereo pipeline, processing the 360 images from Detroit. In a pre-processing step, we leverage semantic labels provided by our state-of-the-art panoptic segmentation pipeline. This is used for masking dynamic information in the images so that we can exclude feature extraction and matching in these areas throughout the 3D modeling pipeline. We use a variant of OpenSFM to generate a sparse point cloud from around 15,000 images, generating a single reconstruction. The video shows the resulting sparse reconstruction result, where camera tracks and the camera frustum of 360 views is split into 6 perspective views with a common camera center. The magenta lines show the overlaps for one camera between different views, which are used to build constraints in the reconstruction process and are making it more robust. Densification of the point cloud is done by using a modified version of the Calmap multi-view stereo pipeline. We use regular patch match stereo from Calmap to generate depth maps and normal maps. Calmap generates confidence maps by looking at the normal and depth maps, assuring consistency between photometric and geometric modes and across views. For the fusion step of the dense point cloud, we also project the semantic 2D labels onto the 3D point clouds as shown in the video right now. The depth maps produced from patch match stereo are further processed on a per pixel basis to remove noise. What we do is to apply a cleanup or filtering process, which is similar to the fusion of the 3D points mentioned just before. Since structure from motion is operating at large scale, the resulting reconstruction is already quite accurate from GPS information alone. However, to improve the quality further, we are ingesting ground control points with geosurveying quality, which means they are measured at sub-centimeter positioning precision, and include them as additional constraints in the reconstruction pipeline. We are annotating an undisclosed set of points on different photo-identifiable objects in our imagery, like the manhole shown above, which we can follow across multiple images in a given image sequence. Since we will not reveal the distribution and actual amount of ground control points, I will not provide additional details about how we capture and ingest them. Area LiDAR is made publicly available from USGS and has been captured with an airplane scanning the Detroit area. The average point density is 4 points per square meter and at an accuracy of 2.55 meters at the 90% confidence interval. Aerial LiDAR provides additional complementary information covering rooftops and regions that are typically not visible from the driving perspective. We additionally provide CAD model information, initially focusing on the downtown area of Detroit. This is typically provided as 3D mesh information with coarse semantic classification into roads, trees, building, terrain, water, and vegetation. We are currently working on obtaining annotations between prominent points on the CAD model data, like distinct corners of houses, and corresponding points in the street level images. So far, I have shown some of the different data modalities we have collected for Metropolis. To enable cross-modal data usage, all of the 3D-based modalities have to be aligned, which is a major problem to be addressed. Hence, this alignment step affects the overall 3D data quality comprising street-level LiDAR, captured with a Trimble LiDAR scanner, aerial LiDAR we are using from USGS, the multi-view stereo reconstruction, and CAD models as shown before. We're using a robust version of ICP, so iterative closest point, which always uses the SFM point cloud as target point cloud for the registration process, since this includes information from the ground control points I've mentioned before. In this way, we can establish links to other modalities. The video on the top right shows the multi-view stereo point cloud in color, and then we toggle the CAD model represented as point cloud used during the alignment process. Eventually, we repeat these steps for aligning also the different LiDAR modalities, like street level LiDAR and aerial LiDAR. Once we have the alignment completed, we can create, for example, different depth representations from CAD models, multi-view stereo, or aerial LiDAR, as shown in the video on the bottom. In the next part, I'm going to talk about the dataset extent, as well as the different types of human annotations we have conducted on 2D and 3D data. The city we cover first in Metropolis is Detroit, and this map shows an overview of the area of our current dataset. Please note that this area is not yet final. In particular, the dark blue region is still growing, which highlights where we have the most dense human annotations in place. The approximate statistics are mentioned on the slide and show the overall extent and regions where we make different data modalities like the aforementioned street level LiDAR, area LiDAR, and other types of RGB imagery available. For 2D annotations, we use the same 32 megapixel high quality 360-degree images as shown for the image-based reconstruction before. The type of annotations are 2D bounding boxes and object tracking information. In addition, we annotate object properties such as occlusion status, depending on the type of object class that is being annotated. The class label set of instance-specific annotations matches the one of Mapillary Vista's version 2.0, and 37 of them are used for evaluation. We want to preserve compatibility with Vistas and to encourage usage of both datasets for 3D semantic mapping research projects. To highlight the actual complexity of annotations, here I'm showing a zoomed version of the 360 image before, and we can see the region contains many different and small street-level objects. Let's dive a little deeper into the actual annotation tools we've built and used. The developed UI is integrated with the Mapillary platform, so we are able to annotate data across sequence recordings. We additionally include annotations across multiple data modalities and viewpoints like aerial imagery or ground control points. Let me show you an example how this interface looks like to annotators. So here we see an interactive version of the tool, how it's being used for the actual annotation process. We see all the 2D bounding boxes annotated in the main window, together with the preceding image from the sequence on the top right for object track continuation. For example, we can step through the sequence here. We also have the availability of jointly viewing all annotations for a single object track, together with further meta information, like in the case for the car here, that it's, for example, partially occluded, that the front or back classification is ambiguous in this case, or also that it's a moving vehicle. The bottom right window shows the aerial view on the scene, enabling cross-modality annotation, which is some form of anchoring of local street-level data with more global aerial information. This slide gives some preliminary information about the number of object instances and average track lengths for which we have 2D annotations in Metropolis. So we can see that on average, we have 75 objects per image and roughly 10 detections per track that can be used for learning object tracking, detection and or tracking algorithms. Here is a video showing a visualization of the 2D annotations provided in our dataset. The color coding also indicates the tracking data, so basically a color doesn't change unless an object instance is changing. We also generate panoptic segmentation results for Metropolis. Panoptic segmentation is the task of segmenting things and stuff where things are all countable objects like cars or traffic signs, and stuff is everything else, for example, the road or the sky. In Metropolis, we use the human annotated 2D boxes as input for our model's instance segmentation head, so we're bypassing the 2D box proposal generation part of it. Consequently, we end up with instance segmentation masks delineated by human-drawn bounding boxes, together with associated confidence information coming from our predictor. As actual model, we're using our state-of-the-art panoptic segmentation, which is described in the next slide, and which is also going to be presented as an oral later in the CVPR main conference. Our two contributions in a nutshell target how to more effectively train a panoptic segmentation network in a crop-based training setting. While crops enable us to preserve fine-grained details and thus detect small objects, the large objects in the training data are over-proportionally often truncated by this cropping process. We fix the consequences that prevent the network from learning the actual extent of large objects by means of a novel crop-aware bounding box regression loss shown on the left. Our second contribution, shown on the right, corrects the imbalance of supervision that is typically provided in a multi-scale detector architecture like in feature pyramid networks. These networks learn to detect small objects using high-resolution features and large objects using low-resolution features. However, due to the imbalance of object sizes in the training set, the supervision for different scales is skewed as well, which typically leads to poor generalization. Our instance scale uniform sampling approach is a simple way to flatten this distribution by augmenting the training data so objects are shown to each scale of the network. Here are some of our high-fidelity segmentation results obtained from our state-of-the-art panoptic segmentation network. Let's move on to the 3D annotations. For the 3D annotations we provide, we leverage on existing 2D annotations and the point cloud data discussed before. The first classes with such annotations are parked cars, traffic lights, junction boxes, and column poles. The task is much more difficult than 2D annotating, as we need to assess the 6 degrees of freedom posed per object. We want to capture the degree of difficulty in terms of annotator uncertainty, which is why we have individual objects annotated multiple times. This is also shown on the image on the right. The agglomerated boxes can be used in conventional ways of assessing 3D box detection, but we take this a step further and also include uncertainty from the annotations in the evaluation process, which I will be describing later. Here is an example of the 3D annotation UI we are using, leveraging a 2D box annotation obtained from the tool shown before and the corresponding crop point cloud data we require for the 3D box annotation task. We show how we visually transfer information from the 3D points to the 2D view on the left, enabling annotators to delineate the final 3D box annotation within all given modalities. On the bottom left, we see an example for an individual object. The thick orange box is the final agglomerated result, produced from the individual annotations shown as thinner colored 3D boxes. So one of the motivations why we keep several 3D annotations per object is the increased complexity of the task. Working with real-world data means that we need to deal with potentially corrupt data, missing or overly sparse point cloud information, annotation errors that are due to fatigue of annotators, and many other potential issues. What we found to be particularly helpful to improve the quality of 3D annotation results is to compare the produced 3D annotations from one view with its projection into another nearby view where we also have 2D boxes as annotations available. In this way, we can quickly and automatically identify issues or outliers and improve the final annotation result in an iterative way. The example shows how a reasonably well-matching 3D annotation of a column pole in the left image can be produced, but it reveals issues when we compare the projection in the nearby view. Here's another video where we see the annotation results for our 3D box annotations, showcasing, for example, the large variability in object sizes that we have. The next data modality are aerial images. True ortho images, which we also register to the available street level images within the same tool shown before. As we have also ground control point correspondences available in the street level images, these points enable us to additionally propagate this information to the aerial image modality. Finally, I want to mention some of the extensions with consumer-grade data, which the Mapillary platform provides at scale, and which we are aiming to integrate side by side with the high-quality data and annotations shown before. We plan to leverage metrics such as reprojection error when integrating new consumer-grade images from the Mapillary platform in the metropolis area. This will ideally help us to determine if new images need further revision before being added to the dataset. One of the key insights we hope to gain here is to how does lower quality data impact the quality of the final reconstruction result and eventually the map making results we're aiming for. As an example of how consumer-grade data is inflowing at this region in the Detroit area, we show some statistics as a function of date and contribution of individual anonymized users. As can be seen, such data flow is covering different times of the year and makes Metropolis a truly exciting dataset. In the next part of my I will present some initial benchmarking tasks and results. Please note that these were produced based on a subset of annotations and are not yet fully conclusive. On the top left is an image that shows the initially used data split for all our described tasks. Here I will cover 2D object detection and tracking, based 3D object detection, single image depth estimation, image retrieval, and based matching. This also means that we haven't yet added many of the exciting tasks Metropolis can support in the future, including cross-modality learning, sensor fusion, aerial matching, and many more. Let's start with the object detection and tracking task, which is well known and has been for some time. However, the type of data we work poses particular challenges. The nature of equivocal images makes image content to be wrapping around a full 360 view.
Yes, I'm checking.
Each of these images. Consequently, the annotations are wrapping around. An example is given a purple crosswalk spanning from left to the right. Another way to be seen is this image, where we center the crosswalk in the middle as opposed to photos before.
Just double check. Can everyone hear my voice? Is there any break?
No, there's no break in it. But the videos, the audio is weird on the video.
Oh, okay, yeah. Maybe it's the recorded video, but we'll just continue play.
Yeah, it's this video.
It's an uncommon scenario in distinction tracking datasets will need to be adopted for in the development of new algorithms dealing with this. Another interesting challenge is posed by the very high resolution. We have 4,000, 8,000 pixels per image.
Maybe we should stop this, and I can just try to take it from a live perspective. This is somewhat not ideal.
Oh, sure. Go ahead.
All right.
I'll just stop sharing.
Hold on, please. Can you see my screen?
Yep.
Yes.
All right. And can you hear me?
Yes.
All right. Then let's try this again. I'm really sorry. Apologize. All right. So in this part of my talk, I will present some initial and preliminary benchmarking tasks and results. Please note that these results were produced based on a subset of overall annotations and are thus not yet fully conclusive. On the top left is an image that shows the initially used data splits for all our described tasks. Here, I will cover 2D detection and tracking, image-based 3D object detection, single image depth estimation, image retrieval, and patch-based matching. This also means that we haven't yet addressed many of the exciting tasks that Metropolis Good, let's start. Which is in itself a well-known task and has been studied for some time. However, the type of data we work with poses particular challenges. The nature of equirectangular images makes image content to be wrapping around as we capture a full 360 view with each of these images. So consequently, also the annotations are wrapping around. And an example is shown here in this purple crosswalk, spanning from the left to the right of the image. Another way to look at this scene is here, where we center the same crosswalk in the middle as opposed to the borders before. Having such a setting is a quite uncommon scenario in existing detection and tracking datasets, and will need to be adopted for in the development of new algorithms dealing with this task. Another interesting challenge is posed by the very high resolution. So we have 4,000 times 8,000 pixels per image, and thus see a large variability in the object sizes that need to be handled. As shown before, we have a label set of 70 object classes, and on average see 75 objects per image, with a mean track length over 10 images. So as a baseline, we are evaluating our CVPR 2020 work, which was providing a solution for multi-object tracking and segmentation. In our case here, we strip the algorithm down to a multi-object tracking solution, essentially leveraging a faster RCNN architecture with a tracking head as shown in the red building block in this figure. Details can be found in our paper, referenced on the slide, but the main idea of the tracking head is really to generate a distinctive object signature by means of an embedding vector, which can be used to re-identify the same object over time and throughout a video sequence. The initial results we are providing start with AP, which is the standard measure for object detection performance. Even though it is difficult to assess this number in isolation, it is close to what a state-of-the-art detection algorithm delivers on mapillary vistas, so we expect about the same degree of complexity in the Metropolis dataset. Moving forward to the tracking-specific metrics, we report MOD-A and MOD-P and IDF1. MOD-A describes how well we can follow the position of objects across frames, while MOD-P addresses the localization of objects. We can see that MOD-P is already quite advanced, but MOD-A still has room for growth, which is what we want to see for a new dataset. We believe that this is due to the challenging scenario given by the large number of objects and classes available in Metropolis. Another challenge is that our image sequences come with much lower frame rate than what a conventional video would provide. In fact, our images are captured at a sampling rate of 1 image every 5 meters, and consequently, the appearance and locations of objects can change more significantly across frames. This video shows some of the initial results we obtained with this architecture. Just to recap, successful tracking is indicated by maintaining the same color for an object's enclosing bounding box. And we can see that this works already fairly well for some of the object categories. However, there's also others, and in particular smaller and fine-grained classes, which are less frequently observed and still need to be improved. We are also assessing the quality of single image depth estimation. So given a single RGB image, we want the model to predict the depth or distance from the camera center for each pixel in the image. As training data, we use the clean depth maps mentioned before and train one of the current state-of-the-art approaches. In this case, it's the from big to small paper. Please note that in this example, we use sparse annotations produced in the cleanup step after running the multi-view stereo pipeline. An example is shown in the middle column of the image on this slide. The quantitative results obtained on the validation set are listed for 2 training scenarios. The first shows SI-log and RMSE metrics when trained on the Metropolis training set, and the second when evaluating a model that is only trained on the Kitty depth dataset. Both measures are error measures, so lower numbers are better. While it is not surprising that training on Metropolis leads to lower errors on its validation set, the actual magnitude is still quite high when compared to where, for example, the state-of-the-art is at the Kitty dataset right now. Future experiments we plan to run in the domain of depth estimation will be learning from depth maps that are generated from the CAD model data, or learning to estimate dominant planes in images given our CAD model information. The next task we discuss here is monocular 3D object detection. So given an RGB image and input, we want to regress a 3D bounding box for each detected object, parameterized by position relative to the camera in 3D space, the dimension of the box, and the rotation of the bounding box. This is an ill-posed problem due to the lack of depth information in the monocular setting. A way to work around this is to leverage prior information about the object category during the learning process. So this slide here recaps the available 3D annotations as mentioned before, and also highlights some of the challenges in our data for the 3D detection problem. One challenge with particularly strong impact is the lack of 3D annotation for driving cars, which we actively excluded from the annotation protocol. During training, however, this might introduce false negatives as supervision, which we of course want to avoid. Our way to address this in 3D object detection is to leverage information available from the 2D annotations, which we also have for moving objects available. This additional data enables us to put a filter for consistency checks in place, where we project the 3D boxes onto the 2D image and verify, for example, its property to be a parked car. Finally, the baseline we have built evaluates on 4 object classes, which are parked cars, junction boxes, column poles, and traffic lights. We will revisit the importance of the multiple annotations per 3D object later, when I'm going to address our new benchmarking ideas. As a baseline, we use our state-of-the-art monocular 3D object detection approach called MONODIS, which was published in PARMI last year. Given an RGB input image, a DNN is used for initial feature extraction. Then a 2D detection module produces 2D box hypotheses. The features belonging to each of these detection hypotheses are then furthermore fed to a 3D detection module, from where we regress all the required quantities that produce the final 3D bounding box results. I am skipping the details here, but all information is provided in our paper on this slide. So here are some of the very first results we have obtained with our MONODIS 3D detection baseline. For evaluation, we adopt the AP and APH metrics proposed in the Waymo open dataset paper. These are average precision metrics defined similarly to the 2D case, but using intersection over union between 3D bounding boxes to match predictions to ground truth. APH further extends AP by weighting true positives by their heading error, providing a measure of orientation accuracy, which is otherwise missing from AP. So the numbers shown here are extremely low for all but the car category. The reason why these results are so low is because even minor issues of the depth positioning of a 3D box, and we're talking about a few centimeters here, may have a major impact on this AP score. Since we're dealing with relatively small box extents in all classes except for cars, this effect is even more amplified. We are still thinking about revising the final metric to be applied here, so that we can better capture the quantities leading to misplaced 3D detection. Finally, I also want to mention that the provided scores already include the uncertainty about ground truth annotations, and I will describe later how this was done. Let's continue with image retrieval next. Our first benchmarking results confirm that Metropolis also makes for a challenging image retrieval dataset. Image retrieval is a more coarse version of the localization problem and requires to identify if 2 images of a given place show the same scene or not. In relocalization instead, the task is to recover the full 6-DoF camera pose. In Metropolis, we are not focusing on landmarks that show overly well-captured or touristic regions, but rather take image pairs from the city which often look very similar and thus make the retrieval task very challenging. In the examples shown here, each column could or could not represent a matching pair. So at this point, I would usually ask the audience who knows which one is the correct matching pair. There's only one. But I don't see right now the Zoom window, so I will resolve this riddle. Yes, it's the rightmost column, which is the only proper match for the retrieval task. And you can see that the building centered on the top of the image can also be seen in the far back of the bottom image. So as retrieval baselines, we were using a net-VLAD architecture, and the obtained MAP scores for the 1 and 10 nearest neighbors are in the 40 to 60% ranges. The last task I'm showing here is patch-based matching, where the goal is to learn invariant descriptors for patches from different views from certain points. We use large-scale SFM to extract patches around interest points, given individual feature tracks that were identified in the mapping process. We don't normalize the patches with respect to their computed scales, which leads to a challenging dataset of local patches, something that is very important since most of the previous datasets are already quite saturated in terms of results, as shown for the phototourism example above. The scores are false positive rates, which means that lower scores are better for an algorithm. So let's come to the final part of my presentation, where I present some of our ideas and solutions aiming at rethinking how we can do benchmarking in Metropolis. So the first thing we want to do is we want to break the positive reputation that the term ground truth enjoys in many datasets. Indeed, ground truth provided by humans is error-prone because of many different reasons. Annotators might have a different interpretation about an annotation task. They might be tired and therefore less precise over time due to monotonous workflows. Or the annotation tools might not provide all the required support. In Metropolis, we acknowledge that there will always remain uncertainty in the ground truth if it's provided by humans. And so we try to think how we can incorporate this uncertainty into the evaluation metrics. The second point we address is something that we call bias to elect a winner. Many, if not all, benchmarks promote a single objective to rank methods on their dataset. And what many of us have probably also observed in the past is that the research community is usually pretty good at optimizing this single objective in order to claim that their method is the best. However, for many computer vision tasks, we can provide multiple metrics to quantify the quality of an algorithm. Even if multiple measures are mixed into a single one, this can lead to a bias by favoring some metrics over others. As a result, we again end up with that bias to select a single winner, which we want to leave behind in our Metropolis evaluation framework. Let's start with the idea of integrating uncertainty into our evaluation metrics. So the goal is to avoid penalizing or rewarding of algorithms in case of uncertain ground truth annotations. So for example, an algorithm could just be lucky and match an annotation result by chance, receiving a reward in terms of improved scores. So in order to avoid this, we treat the ground truth for an object as a probability distribution and compute an expectation of the metric instead. So the example here shows a 2D bounding box detection task, where the dashed box is a prediction, and the differently colored boxes show the different ground truth annotations. When now computing an uncertainty-aware metric for our prediction, we compute the 2D bounding box metric against each of the ground truth annotations and take an average. If the ground truth is uncertain, which means that the ground truth bounding boxes are spread out rather than peaked around the true bounding box, an algorithm will not be able to obtain high scores. The 3D detection results presented before have already been taking uncertainty about the ground truth annotations into account. We replaced IOU computations used for matching ground truth against predictions with a corresponding expectation computed against the probabilistic ground truth. The same expectation is used as a replacement of true positive counters when predictions are matched against the probabilistic ground truth in both the AP and APH metrics that I've showed before. Selecting a winning objective for a dataset makes election of a winner easier, but we might not be able to capture the relevant aspects of an algorithm for a given task. Even if a single objective would be the consequence of combining multiple metrics, this implicitly biases research towards improving some of the metrics rather than others. We propose to drop the need of electing a single winner by means of taking only a single metric into consideration. Thanks to this drop, we avoid putting different metrics on the same scale, which technically might not be comparable at all. For multi-objective evaluation, we leverage the concept of Pareto dominance known from game theory and optimization. So this is, for example, shown here on the top right of the slide. And essentially, we say an algorithm A is better than B only if A is not worse than B on all objectives, and if A is strictly better than B on at least one objective. If this is not fulfilled, we cannot claim that an algorithm A is better than an algorithm B. Let's move to this illustration here on the bottom right and assume that we have an algorithm A here, and we are considering two objectives, objective 1 and objective 2. The green area on the top right shows the area where we can say that an algorithm would be better than algorithm A. On the red area below, however, we can only say, or we can say that these algorithms are worse than A. For the remaining two areas here, we can actually not draw a reasonable conclusion. Now, through this relation, we end up with a partial ordering of algorithms. An arrow, for example shown here, represents a dominance relation where an algorithm is better than another one. Conversely, we can have multiple winners if an algorithm doesn't have another algorithm that's dominating it. Finally, the ranking of an algorithm is given by the path from this position to a given winner. Now, since for the Metropolis dataset, we do not yet have many algorithms evaluated, we took a snapshot of the Kitty 3D object detection leaderboard to compute a multi-objective evaluation example. Kitty 3D evaluates 3 different objectives, categorizing an algorithm's performance on easy, moderate, and hard examples. Each node in this graph represents the ranking in the original leaderboard at the time of taking the snapshot. And if we apply our multi-objective evaluation, we actually end up with several winners, all shown on the very top here, according to our definition before. Interestingly, there was one entry which was originally on position 46 of the leaderboard, which we are now actually classifying as a winner. The reason is that this algorithm was the best performing one on the easy category. And finally, we can see how the ranking develops and how this partial ordering takes form for all entries on the entire benchmark. Studying such a graph is an interesting thing to do on its own. So to summarize, today I've introduced the Mapillary Metropolis dataset, which we've designed as a city-scale framework for multitask benchmarking of semantic 3D mapmaking. I have talked about our vision for using this dataset in future map building research projects and went into details about the dataset modalities, how we have aligned them into a unified reference coordinate system, how we have created annotations in 2D and 3D, and how we leveraged state-of-the-art object recognition models for additional data generation. I have also introduced a number of baseline tasks and provided corresponding results, revealing the potential of Metropolis for developing the next generation of map-making algorithms. Finally, I have touched base on our novel ideas for incorporating ground truth uncertainty in the benchmarking process, and how we believe that multi-objective evaluation of algorithms can overcome biases due to electing winners based on a single primary metric. Finally, I want to thank everyone for their attention, again for the invitation to speak. And I'd like to call out that we're hiring in many different locations, including Zurich, Switzerland, in Boston, but also in Menlo Park. So please reach out to me either with a message afterwards here or on LinkedIn if you're interested in joining as a research scientist, research engineer, software engineer, or also as a research intern. Thank you very much.
Thank you very much, Peter, for your presentation. I know there's a break in the middle and then you take it over for live. It almost feels like nothing has been changed. Thanks very much for your presentation. The live just been as good as the recorded. So let's open up the question for the audience. And then we have about 7 minutes, but we could actually expand a little bit if people can stay, because next session is actually a break. So let's open up the questions for anyone who wants to ask Peter.
There's actually a question in the chat from before. And this one is, how do you use the bounding box annotation tool for the road annotation? So the UI that I was showing before was designed actually strictly for the instance-specific object classes. So everything that belongs to stuff categories, we have not been actively annotating with humans or with human efforts. So we do, however, provide segmentation results, but only by means of machine-generated ways like the panoptic segmentation approach I've shown before. So everything that belongs to a stuff category, and that includes, for example, road or sidewalk or sky or building, all these classes are completely automatically generated and provided as machine-generated segmentation results together with the confidences that we have. Maybe another thing that hasn't been mentioned yet in context of the annotation. So what we usually incentivized annotators to do was to provide bounding box annotations by means of extreme point annotations. And extreme points, they slightly differ from standard bounding boxes. So what people are usually encouraged to do is for a given object, people should click on the extremal points in terms of where a bounding box would be touching the mask of the corresponding object. And in this way, we can also get additional constraints for mask generation later, because we know that these touching points also actually should be part of the segmentation result.
Thanks. Thanks for the presentation, Peter. I had a question. Maybe, by the way, you answered it because I was offline for a small part. You mix different sensor data, and especially with the aerial, this might be from like a different time, right? Did you need to kind of handle this because you, if I understand correctly, that's mainly for the 3D models, but did you need to check for kind of changes that happened during the time of the different sensor recordings?
Yeah, this is a really good question. So many of the modalities that we're bringing in this unified reference system are actually from different times in general. So that also applies for the different recordings of the street level scenes. So some of the scenes have been captured multiple times, twice, 3 times, and also over a period of a few weeks or even months. So there is in general a kind of potential change in the data that we have, and where we are currently still working on how to integrate this information about change. Partially, we're of course trying to leverage as much kind of machine-generated insights as possible. One of the things that I've mentioned before was, for example, that we try to look at reprojection errors, which obviously isn't a really good match for the aerial LiDAR question that you had. But for adding new information in terms of images, that's at least giving us a rough kind of indication which data we should preferably look into and which we can kind of leave as is for now. On the aerial LiDAR, since we're trying to fill in a lot of the gaps and a lot of the holes as well, what we try to do here is also to look at kind of local matching scores. So we do get to some extent information about the alignment quality across different modalities, like for the street level LiDAR and the aerial LiDAR. And we're trying to see if we can, for example, look with our QA system into those regions in a specific and preferred way. But you're right. I mean, it kind of ties into this problem of change detection. And doing this in an automated way is one of the greater goals that we plan to study with this data set.
Maybe then a follow-up question, if that's allowed, looking at the chair. Yeah, I think so. I can also, by the way, open the video. So would you think then that would also be kind of maybe part of the benchmark to maybe actually have change detection, or will there not be enough kind of changes to make this interesting?
So we actually hope to really be able to study change detection on top of this. So that's also why one of the kind of core contributions that we hope to see with this data set is that as more data comes in on the Mapillary platform, we hope that this data can be gradually added over time. So we would have a natural inflow of new data from where we could hopefully get a lot of good examples on, what change detection actually means. So to my knowledge, there is no really good and solid definition of how change detection should be defined. There's many things, including some of them that you were mentioning earlier in your presentation. Like what happens with an object that you just don't happen to see because it's occluded right now? It's probably still there, right? But if you don't see it, how do you deal with it given a certain input that you might have available? So in general, yes, we want to be able to address this, but it's this idea of generating a living and breathing data set. This is something that it's not easy. I mean, a lot of open questions are still kind of on, and we hope to solve at least a decent set of the questions along this study process.
Okay, thanks.
That's a good topic for next year. We can actually bring up another data set and maybe set up a challenge for change detection.
That would be great.
We have another question online from Barbara. Why don't you use the point cloud for annotating 3D objects and then transfer the label to 3D box in the image?
Yes. This is actually what we do for the 3D object detection, for the 3D object annotation. So we use both modalities, the 2D information that we have already for all of the objects and all of the object types with different properties as well. But for the 3D object annotations, for example, when it comes to cars, this is a very specific setting that we have in this data set. So the kind of capture setup that was used to generate or to collect the initial data in terms of the images and the street level LiDAR, it's not a usual or conventional self-driving setting where the LiDAR would kind of also be able to assess the front-facing objects like moving cars. So instead, we have a scanning LiDAR approach that's kind of having this Trimble LiDAR setting where we do scanning of back-facing content, which is more often used in the mapping kind of domain and scenario. However, this also means that we don't have valid LiDAR information for the moving objects like cars. And due to this setting, we were deciding to kind of take this hybrid approach where we have 2D annotations, which are of course also faster and easier to get, versus having 3D annotations for all of the objects. And that kind of prevented us from taking this direction that you were suggesting here in your chat.
Okay, any other questions from the audience? I have one question, Peter. This is a great data set and also a lot of efforts put together, multi-models together for this data set. However, do you have plan to expand it to other cities or countries? Because it seems like it takes a lot of effort to make Detroit working, but also we understand Detroit might have special kind of geographical information that's different than, say, Munich or Beijing. So is the plan to continue build this and expand it?
Yes, this is a great question. So the answer is probably that we try to learn initially from what happens or what we can kind of make better based on the Metropolis data set in Detroit for now. But really the larger and kind of more far out goal would really be to see how can we generate a data set that would include a lot more diversity, a lot more appearance change by taking on other cities. And we wouldn't even have to necessarily stop there, right? So another very interesting property would be to add a synthetic city side by side, where we can know that a lot of the data modalities are potentially much more easily generated. But if we had everything in a joint and unified system, then maybe one could also study ideas like domain adaptation or domain transfer from certain knowledge. All of these are open questions. For now, we don't have enough with what we've done. I think there's plenty of opportunities to extend this, and we will definitely keep you posted.
Thank you. We have more questions coming from online. One is, can we share the link of the data sets somewhere?
Yes, so I was mentioning that a lot of the annotation processes are still ongoing and that we're still expanding the data set. So we of course intend to do that as fast as possible, and then we'll keep the community posted about the next steps.
Okay, so this is just a preview right now and to give people like idea what this is. Very exciting.
Yes.
Another question from Angela Young is, if you have a bling bling building like mirrors on the street, then how the street view image, how do you remove the fake car detection on buildings on the image?
Okay, let me read this again. Building like mirror on street view image. Then how do we remove this fake car detection building on the image? I'm not entirely sure if I.
It's like, if you have, say, a mirror or something that actually shows a car on it, on the building, do you have a way to remove it from there? Because it's a fake car, it's not a real car.
Okay. From the annotation protocol, we have been instructing annotators to of course, not label objects which are not physically in a position or at the position where we would expect them to be. And that usually applies to a set of dynamic objects. So we don't really have annotations for such fake objects as part of the data set. Conversely, we have not explicitly annotated them with another label. So that could have probably been a good idea to do, but we decided for now to really restrict the annotation process to objects that we actually see and that are actually able to grasp for a recognition system.
Cool. Any other questions from the audience? I'll take it as a no. And thanks very much, Peter, for your presentation. And we concluded 2 presentations this morning, and we will have a 1-hour break from now to 1 p.m. Eastern time. And also for people who have lunch or breakfast, whichever you prefer. So we'll come back at 1 p.m. Eastern time. And I'll keep this meeting up, but I'll not record, I'll just keep it running. And then people just feel free to jump to other things and come back to us at 1. Thank you, everyone.
Thank you. Bye-bye.
Okay, welcome back, everyone. we're going to have the next presentation given by Raquel Urtasun, who's the CEO of Waabi and also the professor at University of Toronto. And she have a pre-recorded video, and we'll play that video and then she'll join later in the Q&A. So let's start.
Hi, my name is Raquel Urtasun, and I'm the founder and CEO of Waabi. Today, I'm going to talk about mapping for self-driving. But before I do so, let me tell you the exciting things that we are doing at Waabi. Self-driving is one of the most exciting and important technologies of our generation. Once solved at the scale, it will change the world as we know it. Since the DARPA Grand Challenge in 2004, the self-driving industry has made meaningful progress, but commercial deployment is still limited to very simple and small operation domains. The traditional approach to engineering self-driving vehicles results in a software stack that does not take full advantage of the power of AI, and that requires complex and time-consuming manual tuning. This makes scaling costly and technically challenging, especially when it comes to solving the less frequent and unpredictable driving scenarios. Building off the lessons of the last 2 decades, Waabi is tackling self-driving in a new way that fully unleashes the power of AI. In particular, our AI-first approach leverages deep learning, probabilistic inference, and complex optimization to create software that is end-to-end trainable, interpretable, and capable of very complex reasoning. This, together with a revolutionary closed-loop simulator that has an unprecedented level of fidelity, enables testing at the scale of both common driving scenarios and safety-critical edge cases. This approach significantly reduces the need to drive testing mass in the real world and results in a safer, more affordable solution. Our first use case is long-haul tracking, where there is a chronic shortage of drivers and a need to enhance safety. We are backed by the best-in-class investors in terms of big technology, logistics, and the thriving Canadian ecosystem. We launched the company last week, announcing one of the largest Series A in Canadian history. We have offices in both Toronto and San Francisco. Come join us, we are hiring. Now let's get back to the topic of the workshop. Let's get back to mapping. There is really 2 types of maps that are used in self-driving, topological maps as well as high-definition maps, and they have different usages, whether it's to route the vehicle with a general route or to really drive precisely in the environment. We're also going to see today what happens when the map can potentially change or you might lose localization, and there is a requirement for doing online mapping. So we will review some techniques into how to do so. Finally, we will look at how to use cooperative multi-agent mapping in order to create maps at the scale, city scale. All right, so let's get into topological maps. Topological maps have actually attributes that are pretty interesting, and they have very different flavors. They consist of things such as the road topology, typically with lane center lines. Sometimes they also include lanes, although these are typically in these maps not super precise. Building footprints, parking lots, or just rough information such as the number of lanes or the direction of travel are also common attributes employing this. PDOs, which are locations where you can actually park your vehicle or stop in order to drop a passenger, are more and more common these days, particularly with ride-sharing applications. Now, if we look at the use of topological maps, there are really like 2 use cases in terms of self-driving. First, they are employed in order to decide what are the routes that I should send the mapping vehicles in order to collect data prior to creating these maps. They are also used inside the self-driving vehicle in order to generate very rough routing, such as in order to go from point A to point B, what is the series of roads that I should actually take? And you can imagine that this is actually fairly similar as how humans utilize routing, for example, when you use your favorite GPS or Google Maps app. Now, in order to create these road topological maps, there is many different types of devices that one can use to obtain the road sensor data from which to estimate these maps. One can use, for example, webcams, which are very cheap, and potentially these days millions of vehicles that are equipped with them. So this data is actually readily available to potentially have automated methods to create maps. Another common way to use these maps is by employing or seeing the world from above, whether it's drones or planes. These are potential vehicles that one can employ to collect the data. The advantage of here being that we have a really bird's eye view perspective of the environment. One of the problems being that we might see actually occlusion, for example, by trees or other vegetation, or even buildings that might make building these maps a difficult task. Of course, one can also employ self-driving vehicles and the road sensor data that they capture in order to build these maps. Now, it's much more difficult to build this at the scale because these vehicles are very expensive and they don't necessarily exist at a very, very large scale. We only have typically 100 of these vehicles at most. Now, let's review how we can employ automatic methods to try to extract the topology of our roads. There is really three different types of approaches that have been developed in the literature. On one side, we have segmentation-based approaches that utilize heuristics in order to convert segmentation to the final outcome. We also have energy-based methods as well as neural networks, which are more common these days. So let's give a little bit more details into all of these three approaches. If we look at segmentation-based approaches, it's actually very typical to employ aerial images or satellite images as inputs, and then basically utilize a segmentation-based approach to create some soft representation of where roads might actually be. Now, the good thing about doing such an approach is that we can employ state-of-the-art segmentation methods, which are pretty powerful. And we can even pre-train them in standard image-based data sets in order to only require very little data to fine-tune these methods, for example, with the aerial images. Now, there are several disadvantages of using such an approach. First, we are dependent on the segmentation quality. And as mentioned, there exists very little level data of aerial images. Furthermore, segmentation is really a means to an end. It's not the end goal. The end goal is to obtain the topology of these roads. So we need to have a post-processing approach in order to somehow extract this information from the segmentation. Now, this is typically done in a very, very ad hoc manner, for example, by doing thinning or extracting the skeleton of the segmentation. And this results in topological maps that have holes, they don't have the right connectivity, and in general are not super good for usage in this application domain. There's been techniques that have been looking at how can we, given the output of a segmentation and some initial topology estimation, how can we get better estimates? For example, by reason about whether disconnects in the map should actually be connected. In the picture here on the right, we see the result of an approach that basically looks at in the vicinity of these disconnects, creates a graph, and basically reasons about whether these different points should be connected. And if yes, it employs a very simple A** algorithm in order to find the closest path to connect the two ends that have a missing link. What this goes one step forward in terms of creating topological maps on segmentation, still doesn't produce the quality that we typically require in this application domain. More sophisticated approaches have been proposed by looking, for example, into energy-based methods. And the idea being that we can create a Markov random field where the states of the MRF and the random variables represent the actual location and topology of the road. This has been used, for example, to utilize OSI maps as input and then obtain cues from aerial images to basically align these maps better and obtain, for example, road width as additional information from these aerial images. Now, the advantages of such an approach is that we incorporate our prior knowledge about the task at hand in the MRF itself, for example, in terms of the parameterization, which is defined with the random variables and the potentials that define the goodness of every state of those random variables. However, typically inference is complex, which means that it might be actually quite slow to do inference unless you use quite some clever tricks, like in some of the papers that we've seen recently. But more importantly, the approaches of this type typically employ handcraft features which do not exploit all the level of sophistication that deep neural networks or the high capacity of deep neural networks that potentially can enable you to get much more precise topological maps. And in general, this doesn't really result into the level of quality required for self-driving. Recently, there has been a different type of approach that basically utilizes neural networks in order to do this task. A natural way to do this is by using a recurrent network, where recursively one is going to output for example, the location of piecewise linear approximations of the different of the polygons that are actually representing buildings or representing center lines. One advantage of this is that we're using learning, and in particular the power of deep learning, to be able to really do pretty sophisticated inference here. However, learning of this type of approach is actually quite difficult, and the variabilities in topologies between different areas is actually something that is pretty hard for these RNNs to actually capture. And when we see occlusion in the image, for example, with these aerial images, we might have quite a bit of difficulties into really generalizing across or connecting things that are heavily occluded. Finally, the last work that I want to showcase in terms of these topological maps is recent work done called NeuroTurtle, work by Tuel, where basically goes one step farther than the simple topological extraction that we've seen before in order to generate new roadmaps. And in particular, the roadmap is considered as a special graph, and by using RNNs, they sequentially generate nodes in the graph conditioned on the already generated graph to obtain a road network. So you can think of this as you are exploiting the context around you in order to decide what is the next node. And this context is not just the image features, it's actually the topology that you have already extracted. And this idea can be quite powerful. The model can also be conditioned on a set of attributes to control, for example, the style of the generation of the road network generated. And as a consequence, one can do, for example, as seen here in the image, generate, say, New York style versus London style, which in Europe versus North America, right? The type that we actually build, the topologies of the city and the roads is very, very different. So let's look at a video of this approach. And what you can see here is like different layouts generated. And in this case, this is done as just a generation process, regardless of, without having any image evidence. They can also show that you can do this in an interactive fashion, which might be very, very useful in order to create new topologies. So we have reviewed quite briefly, but some of the approaches that people have proposed in order to do or to create these topological maps that you will employ, for example, for this general routing. The next thing that we're going to see is how we can go from these simplistic maps to super high quality, high definition maps. And we will touch upon both generating the maps themselves in terms of the geometry, as well as generating their attributes, the semantics that are useful for self-driving. So the task at hand is really to create globally consistent high-definition 3D maps of the world. Globally consistent meaning is that we have a single coordinate system that is global, that really represents where we are in the three-dimensional space. And the idea is that we want to create this at scale, and this scale is typically at least at the city level, because we want our self-driving vehicles to be driving around, everywhere in the environment. Now, in terms of what are the desiderata, the characteristics of the creation process, so there is really like three different things that we need to consider. Typically, the way that these maps are built is by having a fleet of vehicles doing multiple passes around the environment, and then building a 3D map from that environment and then obtaining the semantics. So we would like to have a way to create these maps by having as little passes as possible over the same area, because this capture is actually extremely expensive. We would also like to have low storage requirements once we generate these maps, because potentially we might use them for localization or for our autonomy system. And as a consequence, we need to store them on vehicle, right? So we can't have, like super high storage requirements for those maps. Otherwise, we will only be able to drive in a very small area. Finally, when you look at the task of generating these maps, when you drive around, there is a lot of things in the environment, things that are not permanent. There are things that might be there today, but might not be there tomorrow when we pass around. Things like vehicles, things like people walking around, right? So one of the things that is important when we create these maps is that we remove all these non-permanent elements from the maps. Okay, and we will quickly review also how we can do this. So if you think of the pipeline of building this map, there is really like 4 stages. First, we need to select into where we're going to build these maps. And when this might be actually simple for you, it's actually a pretty difficult task in terms of not only we need to decide what is a good area for the self-driving vehicle to operate, which in itself, we need to understand where potentially, we can make the safety case and where the vehicle will be able to, to operate safely versus, being faced with situations that it cannot handle. Right? So this task is difficult in itself. But also, once we have decided what that area is and the actual routes that we need, the actual roads that we need to map, we need to decide on what is the specific routes that the different mapping vehicles need to do, such that we collect all the required information to later be able to build these maps. Okay, we will touch upon how to actually do this well later on by using an algorithm that is actually communicating between the different vehicles and online trying to route in the best manner. Once we collect the data, we need to build these 3-dimensional maps. So we need to be able to align all this information such that we have like super precise geometry. And after that, we can extract all the semantics and we will look at how we can use a combination of humans and machines in order to scale our ability to basically obtain the semantics. All right, so let's start by looking at the map alignment process and what are the things that we actually need in order to do this task. All right, so I guess the question is, right, so how, given the collected raw data, how come we can build these geometric high definition maps? So it turns out there is actually 3 steps in order to do this, right? we need to first split the raw data into small chunks and fit trajectories for these individual chunks, which is something that can be actually performed in parallel. And this gives us some notion of how we have driven in the environment. And remember that this is really at city scale, right? So we need to do this process in a course of time, in a local manner and then expand to the full extent of the city. So that's what this first step is actually doing. And then we need to align all these small trajectories into a massive global optimization problem, which can be solved, for example, with graph slam techniques. And finally, we're going to assemble all the chunks with this globally consistent map in order to create the final geometry. All right, so what we're going to do next is that we're going to explain the SLAM system, which is able to do, SLAM is standing from simultaneous localization and mapping, that is able to do things like fitting individual trajectories, as well as this global optimization process. And this will depend on whether we run this SLAM system online or offline. And there is different variations of technology if you want to do one thing versus the other. Now, SLAM systems typically consist of a front end and a back end. The front end takes the raw sensor data as input and performs feature extraction to parse the raw input into intermediate representations. Data association is then performed on the intermediate representations to align consecutive frames as the vehicle travels. In addition, the front end is also in charge of loop detection when the vehicle is actually revisiting the same area. And this is important because otherwise we typically have drift, and we need to basically align everything to be as globally consistent as possible. The SLAM front end then passes the process sensor observations to the back end, which basically performs graph optimization to estimate and refine the vehicle poses and the 3D map. All right, so let's look at how this front end actually works. And here I'm not going to give a full tutorial on SLAM. That's not my intention, but just to give a hint into how actually the systems work. Now, the SLAM front end parses and associates raw sensor data to derive constraints between the 3D map and the vehicle poses. The specific implementation of the front end is sensor dependent. Common sensors employed in a SLAM system include LiDARs, cameras, inertial measurement units or IMUs, GPS, as well as wheel encoders. In the self-driving industry, it is common to use all aforementioned sensor types to build high-definition maps. In academia, we typically see SLAM systems that use one or maybe two of these sensors at most. We next briefly discuss LiDAR-based front-end and camera-based front-end approaches. In a LiDAR-based SLAM system, the front-end typically performs 3D registration between LiDAR scans for tracking and loop closure. So given these LiDAR scans, we want to bring them together such that the environment perfectly aligns. This 3D registration can be performed with classical approaches, such as the iterative closure process, or ICP, and some of these variants. For example, there is techniques that actually have an optimal solution to ICP, which are fairly interesting. And there is also learning-based approaches that actually try to make this alignment by basically learning to align by processing or aligning, typically with things like CMS networks, the different sort of LiDAR strips. On the other hand, camera-based front-end process input cameras, inter-camera images to perform post-estimation during tracking and loop detection. And the difficulty here arises the camera is a projection of the 3D world into a 2D plane. And the poses that we're typically interested in are in three-dimensional space. Camera-based front-end can be generally divided into direct and indirect methods. Direct methods such as the famous D-time or LSD SLAM or DSO use the raw image pixel intensities directly and optimize with photometric error in the back end. On the contrary, indirect visual SLAM systems, such as MonoSLAM, PTAM, and OrbiSLAM, represent images as sets of key points with classic feature structures. Image association is performed by finding key point correspondences and optimizing with geometric error in the backend. Generally speaking, direct methods usually use all pixels to leverage all information of an image, which can lead to dense maps and large, expensive, and challenging optimization that oftentimes requires good initialization to converge to optimal solutions, or as close to optimal solutions as possible. However, it is worth pointing out that there exist direct methods such as DSO that use sparse pixels to reduce computational burden. On the other hand, indirect methods typically use sparse key points, which are more computationally efficient. However, the sparse key points do not leverage all information from an image. And as a result, potentially they can have inaccurate estimates or be unreliable at times. Next, we're going to discuss the SLAM backend. Again, very, very briefly. With the raw sensor data, the SLAM frontend constructs a factor graph where the nodes are the parameters associated with the 3D map and the vehicle poses, and the edges are the constraints obtained from the sensor observations. The SLAM backend then takes the factor graph as input and performs graph optimization to join and refine the 3D map and the vehicle poses. The backend graph optimization can be divided into two approaches. The classic filtering-based approach uses typically an extended Kalman filter. The vanilla AKF typically marginalizes all vehicle states other than the current state and results in a compact graph, but it suffers from inefficient graph updates as well as inconsistencies from linearization errors. On the other hand, modern smoothing-based backends generally optimize poses and geometry with non-linear least square errors, but optimization over the entire graph can be computationally expensive and quite challenging. In practice, in industry, you will see, thousands to tens of thousands of cores typically employed to actually do such an optimization. To improve computational efficiency, a smoothing-based backend typically selects a subset of all the frames as keyframes and only performs optimization over them. In addition, sliding windows are also typically adapted to optimize poses and geometry only over a window of the most recent frames. Compared with filtering-based approaches, it was shown that in monocular visual SLAM systems, smoothing is more efficient in if high accuracy is required. Now let's look at how people have integrated learning into SLAM. There are generally two approaches to integrate learning into SLAM systems. Recent end-to-end visual SLAM systems mostly focus on direct methods and use neural networks to jointly learn depths and poses with the photometric laws. Alternatively, several approaches only learn part of the SLAM system. For example, we've seen recent works that have successfully learned the loop closing module of a LiDAR SLAM system, the 2D front-end features in a visual SLAM system, and the keyframe selection stage of a visual SLAM system. These are just particular instantiations of this idea of one can leverage the power of learning, in particular deep learning, in order to potentially be more robust than by using classical or hand-engineered approaches. If we look at self-driving, we might also need to handle asynchronous sensors for a SLAM system. Self-driving cars are typically equipped with multiple cameras to make more observations of the surrounding environment. Existing multi-view SLAM systems all assume that the multiple cameras fire at the same time. However, in practice, the multiple cameras can be asynchronous due to technical limitations or by design. For example, it is very, very common that the cameras can be synchronized to another sensor, such as spinning LiDAR, which this is, as I said, a very, very common setup in industry. To tackle this problem, asynchronous multi-view SLAM formulates a general SLAM framework that accounts for multiple asynchronous cameras. And in particular, needs to infer when every camera fires in order to provide robust estimates of how the vehicle is moving, as well as the map itself. So this has an additional added complexity compared to standard SLAM. The results shown here shows that using multiple cameras and correctly accounting for their asynchronous nature is important towards accurate and robust SLAM in challenging real-world scenarios where we have this asynchronous firing of the sensors. Let me now show you a video of MMB SLAM in the real world, which is this technique that is able to utilize asynchronous sensors. On the top left, we only show the view from the front middle camera, while in practice, the system takes input images from 7 cameras that see 360 degrees around the vehicle. We show the estimated continuous time vehicle trajectory in green and the generated map points in black. Our system successfully estimates its trajectory through the busy streets and manages to close the loop correctly, as you saw in the video. Sorry about that. While the previous example shows maps generated with the camera SLAM system, in practice, when we build these large-scale maps in the industry, we use multiple sensors. Here is a reconstruction of a part of an area facility that we have done in the past, where in particular we use LiDAR and cameras to create these reconstructions. And note that the other thing that we are doing here is that we are removing these non-permanent objects. For example, all the vehicles that were there in the scene. So how can we remove these objects? What can at rescue is actually that we can use semantic segmentation of point clouds. And in particular, we build different generations of technology in order to really estimate semantics in a very accurate way. And the idea for these maps is that you want to make sure that everything that stays in the map is actually permanent. So it's worse to actually leave, for example, a piece of a vehicle of a person that actually to remove a small part of the map. Since we have multiple passes, we will be able to complete these maps with, or when we get all the information together. But having noise is actually potentially quite detrimental. Now, we can use, as I said, this semantic segmentation, 3D semantic segmentation, in order to remove these objects. And next, I'm going to show you the effect that it has in creating these maps. So this is stuff that we did in the past at the ATG, where unfortunately the GIF is not playing, but basically this is you're supposed to see a map when you have permanent elements and when you have transient elements and when you remove them. That is much, much sharper. Sorry about that glitch. All right, so next we're going to look at generating semantic map of the environment. And when we look at the semantics, depending on the use case and the particular autonomy stack that is going to employ these high definition maps, there is many different layers of information that you might be interested in obtaining. From where the lanes, the crosswalks, the intersections, whether there's construction, the signage, conflicts and constraints of where you can drive, or the rules of traffic that you need to obey to, directionality of the lanes, school zones, things like this are typical information that you will see in high definition maps in self-driving vehicles. Now, let's look at what is the desiderata of the characteristics for these high definition maps. First, we would like to have highly accurate semantic labels, because this is important for safety, right? We're going to use this in order to drive in the environment. So typically there is super precise requirements of being, an error of less than 5 centimeters will be quite common in the literature, in the industry. So as you can imagine, this is actually pretty hard to do with automation. Moreover, right, we need to have a scalable approach because we want to create these maps potentially from all over the world. And there is several challenges if you want to do this. First, right, the maps might change, right, from time to time, due, for example, to construction. In addition, the typical mapping process, right, in many companies involves a fleet of vehicles passing over and over and over again the same area, right? So we want to make sure that we actually have solutions that do not require many of these passes, right? So that's challenging, particularly from a dollars perspective. And typically obtaining the semantics is something that is done by hand, where there is a representation typically of a bird's-eye view representation that is created automatically. And then companies have hundreds and hundreds of labelers just basically clicking and putting by hand all these different semantic layers that I just referred to before. So that also is not going to scale, right? This is not something that we can do the entire world. And remember that the world is actually quite vast, right? We are not talking about just one specific area, your neighborhood, or your city, right? Or your province, state, I guess, if you're in the US, continent, right? We are talking about, we want to have self-driving vehicles operating all over the world. All right, so let's see how we can actually try to do such a thing. So thinking that we're going to do everything automatically is a little bit naive, right? Meaning that if we have this very, very stringent requirements because of safety that we have to be we have to have very, very little error, right, in our maps. We're going to wait a long time until we can develop a technique that actually works at that level of reliability. And we would like to still make progress and scale our maps and save millions of dollars. Typically, building one of these maps costs $1,000 per kilometer, right? So think about your city, which has a couple of thousands of kilometers at least, right? So this is a couple of millions of dollars just to create the map once. Right? So we need something different, right? So what we're going to look at is, can we actually build techniques where it's easy to do human in the loop setting, where we will create some automatic version that is already very good, and humans only need to QA or maybe change a couple of things. And this way we can actually get to the level, to the scale that we need in a way that is much cheaper. So let's try to see how we can actually do this. So first we're going to look at the problem of road boundary estimation. So this typically is going to create a definition of where is drivable surface, where you can actually drive and where you can't. And in these high definition maps, one of the things to take into account is that we want structured output representations, typically polylines or polygons. And this is actually pretty hard to do for whether it's classical techniques or modern techniques. Right? Neural networks are really great at estimating a class per pixel, right? Or a class per bounding box or per the entire scene, but they're not so good at doing things such as delineating or having these structured representations. All right, so as I mentioned, right, in the industry, this is typically done by hand. And in academia, right, we've seen a lot of segmentation-based approaches, as I mentioned, the topological part, that are actually not very reliable, that do not have this level of precision. Right, so one of the things that we're going to look at now is, can we use, in particular, convolutional recurrent networks as a tool to try to estimate or trace these polylines to create the location of the road boundaries. So in order to do this, the input to the model is going to be a bird's eye view representation that once we generate these three-dimensional maps, we can render them from the top, and we can render the LiDAR, we can render the cameras, like we can create panoramas, right? Since we have all, thanks to Islam, we have everything, like super precise done in 3D in terms of the poses of the vehicle as well as, the map itself. And then basically the idea is that given this input representation, we are going to use a convolutional recurrent net to estimate where to start drawing one of these polylines and the polyline itself. Okay. And one of the things that actually work pretty nice in practice, if you want to do such a thing, is to create supervision for the network in terms of the intermediate representations by adding, for example, information about things like if I predict the edges or if I predict directions of these edges, this is information that is going to help the network to actually trace into where these structured polylines are. So this is an idea that actually in general for mapping works really, really well. So I recommend you to, if you're interested in mapping, to do such a thing. So let's look in practice into how this technique actually works. So on the left, you're going to see the ground truth. And on the right is the output of our fully automatic system. So it's very rare that you see mistakes. And if you see a mistake, then the human can basically just click. And this, what we call a C-snake, so it can actually recorrect itself from there. So it's super, super amenable to user in the loop. And it creates these structured representations. And as you see here, it can actually deal with very different topologies, geometries, whether it's straight roads, curvy roads, different types of intersections, etc. Okay, so it's, this is one step forward into really automating the process of creating these maps. Now, if you look at what we have done here, we are really just looking at automating the process of creating the road boundaries, right? That give us where is drivable surface. But there is many more elements that we are interested in. So one of the things that we look at is, given the fact that we know where these road boundaries are, can we employ this information to obtain other elements in a way that not only is going to be very efficient, but also is going to be very precise? Right, so instead of, in this case, we're going to look at estimating crosswalks. So instead of trying to draw crosswalks from scratch, we're going to say that given the road boundaries, a crosswalk is defined by basically 2 points on the road boundaries. Right, so this is a minimal parameterization, right? And since we have the road boundaries that are very precise, right, they are either automatically generated or corrected manually by humans, then these crosswalks will actually just align to these road boundaries. So you can treat this problem as inference in an MRF again. So in this case, it's a structured representation. And then we use a deep structure model where basically we learn some intermediate features again that actually going to be very useful for the MRF. And the MRF is just basically doing exhaustive search in a super fast manner because you can use things like integral images and generalization of these integral images and basically placing what the road boundaries are for the crosswalks. Okay, so this actually worked pretty nicely, and let me show you some results. So in the video here, you're going to see the input representation is going to be, again, bird's eye view of RGB as well as later. And on the right-hand side, you're going to see the final predictions of our model, fully automatic. And on the bottom, you see basically the ground truth. So as you can observe, for the vast majority of 95+% of the crosswalks, we don't need to do any corrections. Instead, basically, this can automatically actually draw those crosswalks. So this is an example of how we can really automate this task and then go from road boundaries to also have the next set of sort of semantics. Now let's look into further one more elemental. And in particular, what we're going to try to do here is that We're going to focus on highways for this example, but the idea is that we are interested in now drawing the lane boundaries and drawing these lane boundaries in a way that is super precise, okay? So that we don't need too much or any correction by the humans. And the difficulty of this task is the fact that we're going to do it with big stretches of the highway. We're going to show you images here that are basically half a kilometer. And the difficulty is that we need to look at the space of possible graphs, right? And this is like, there is way too many possibilities, right? So we need to come up with a way to do inference in the space of graphs. And we would like to also leverage the power of deep learning in order to do this. But we want these structured representations in terms of, in the form of graphs, right? And the question is, how can we actually do this? So the idea is that we're going to represent this graph as DAG, right? And this is going to enable us to handle changes of topology, like for example, forks and merges happening in highways. And we're going to enhance this to have some attributes that will tell us whether we need to fork or merge. So let's look a little bit more in details of how we can actually do this. So given a temporally aggregated LiDAR point cloud projected into bird's-eye view, as you see here in the image, we aim to find the maximum a posteriori of the probability distribution over all the possible DAGs, right, directed acyclic graphs that could describe the road. Now, in our model, in order to do this in a way that is, computationally feasible, we are gonna factorize the probability distribution of each DAG. Remember that we don't know the DAG that we see in the image, but we're gonna factorize the probability distribution of each possible graph as the product of the probability distribution of the vertices. Okay, so this is an assumption. And each vertex is gonna be conditioned in its parents with a random variable that has basically 3 attributes. The direction of this vertex given the parent, so in which direction we should be drawing, the geometric position of the next vertex, so the length on that respective direction, and the topological state of the vertex. And this basically is 3 states, where there is no change, a fork or a merge, or we should stop drawing, right? Because at some point, maybe there is no more. Now, the space of all possible graphs is exponentially large. So what we're gonna do here for inference is basically to use a greedy approach where we're gonna construct the graph one vertex at a time, okay? So we demonstrate the inference process here on the images that you see on the right. On the top, we assume that we have already inferred part of the DAG up to this current time step, right? And we have this vertex that you see here, and then we are interested in what should we draw next. So we find the direction for the next vertex highlighted in yellow. And this is going to allow us to extract the region of interest in order to decide where to place the next vertex. Then we're going to infer the position of the vertex in this region of interest. And then we're going to infer whether the type of vertex that this is. In this case, the type is actually there is a fork. And therefore, for the next step, we're actually going to spin up 2 different polylines emanating from this vertex. Okay. So, the fork, right, we will continue drawing the current lane boundary as is and continue emanating things. Okay, so you can repeat this process over and over and over. And this is the way that you basically start drawing your different roads. Now, as I mentioned before, we want to really leverage the power of deep learning. So in order to model these probability distributions that we were doing inference over before, basically we use a deep structure model, right, where the probability distributions are coming out of inference on deep neural nets. Okay, So as a consequence, you use the power of MRFs and you use the power of deep learning as well. So let's see how this actually works in practice. And we are gonna first look at, we train this with only a few examples in highways of Arizona. And then we're gonna test of sort of the same geographic area, but obviously not in the same area, not exactly the same area, but within the same state. On the top is the prediction of the network without any human intervention, and on the bottom is the ground truth. And as you can see, the network does a remarkable job at really predicting these very complex topologies. And remember that for neural networks, really estimating topologies is extremely, extremely difficult. And this network is able to learn to do this with only a couple of hundred examples, which is remarkable. Next, what we're gonna do is we're gonna look at whether we can generalize to different states. So we train only in Arizona, in I-40, and now we're gonna look at can we estimate highways in California? So 280 as well as 101. And as you can see here, right, it does a very, very, it's a bit worse, but it does a remarkably good job at estimating the topology. Now, it has never seen highways with so many lanes. And in California, there is so much traffic, so everything looks very different. But without domain adaptation, without retraining, fine-tuning, or anything, the system is able to generalize really, really well, which is, the virtue of these deep structure models that enable generalization beyond the training distribution very nicely. Now, after the work that he has presented, there has been more work that actually has been based on the kind of approaches that we develop. Just showcasing one work here where they use a very similar idea to, instead of drawing lane boundaries, they draw lane center lines. And center lines are a little bit more tricky because in lane boundaries, typically you have evidence. In lane center lines, you don't. So you need to, the network needs to understand the concept of the center of two things that have boundaries. Okay, and that's in general difficult. So we have without more prior knowledge, potentially this is hard to do. So I think I'm hinting that there is actually potential improvements that you can do if you actually take into account maybe more structure in the output space of what you're trying to do. All right, and these approaches that I was showing you were all estimated from driving around vehicles and then basically creating this rasterized bird's-eye view perspective. But there is no reason that this should be the inputs, that you can use other inputs. So here, what you can see is, in this case, the test track of Uber ETG, and a drone that we just flew. And one of the things that you can observe is that you can actually build these maps in a similar manner, just by exploiting this imagery that a drone can capture. Right, so you don't even really need to drive a vehicle in order to create these maps. You can do it from aerial views. Satellite images is difficult because of the resolution. Typically, it's 50 centimeters, what you will obtain from a vendor. And that, when you want 5 centimeter accuracy, there is no way that you can do it from a pixel being 50 centimeters. All right. So let's look quickly at into online mapping. And one of the things to think about is that even if you have high definition maps, the way I think about maps is really as a sensor, meaning that you shouldn't trust it fully. It might actually have mistakes, whether it's due to localization failures, whether it's due that your maps are not up to date, or maybe you don't even have a map on this particular area. So for safety, in self-driving, you need to have a solution that is able to do driving without maps. And for this, you typically require to do online mapping. Now, this online mapping can also be used to update maps as you basically drive, right? So you can use this technology to remove the need for the expensive manual process. Now, what are the challenges of doing online mapping? Well, as it's a single pass, right? And it's not even a full pass. You're actually starting the pass. So there is very little observations typically. You have occlusion. You have to estimate things at range because in order to drive, you need to see quite far. You need to handle things like construction, right? And you still have these tight requirements in terms of accuracy, and you need to do this online on board the vehicle. So it has to be really, really fast the way to do this process, because not only you need to do the mapping, you need to do the rest of the autonomous system as well. And since you are building a map, you need consistency over time. It's not that you have to do this independently every frame. So this is pretty challenging in general. Now, in the literature, we've seen a lot of works that, for example, when they try to estimate lanes, they estimate these lanes in 2 dimensions. So you will see, an image, right? And then, sort of the estimates in image space. And it looks great, right, in the image. Now, what is important to note is that doing well in the image doesn't mean anything. In order to drive motion planning reasons in bird's-eye view, right? So you need these 3D estimates, and you need to project back into where the ground is. And the ground, very important to note, is that the ground is not a plane. It's a sophisticated, surface. So when you project this, what it looks like a very accurate 2D estimates, and you project it to like this one's, right? And you project it to 3D, you observe that, particularly as you go farther and farther, they are really inaccurate. And this is not sufficient for driving. So instead, we need to really reason in 3D, right? I need to get these accurate estimates in 3D, our metrics in 3D, etc. So there's been interesting approaches recently, and I'm highlighting one particular one because I think it's quite interesting that they actually treat the lane detection problem as a detection problem, where basically one defines detection as well as the anchors, and then is the deviation from those anchors that basically represent what the lanes are. And they have also a way to basically handle forks and merges by predicting to center lines here. So I think this is an interesting approach that is not the most intuitive one, but I think it's quite interesting to leverage all the good work that has been going in detection in order to do good lane detection, which is something that we haven't seen much in the literature. One approach that we did that actually works remarkably well in practice is the following. So what we're going to do now is that we're going to utilize LiDAR as well as cameras in order to get directly an estimate of the 3-dimensional representation where the lanes are. And for those of you that know some of my work, I love distance transforms. So it turns out this is a nice thing that you can predict, that you can use later for motion planning. And the thing that is important is that if you want to use images and LiDAR, you need to put in correspondence these 2 sensors. And just having a calibrated vehicle is not sufficient. You need to know where the ground is because we are estimating things on the ground. And as I mentioned, the ground is not a plane. A plane is too simplistic. Think of San Francisco and Lombard Street, etc. Right? That's definitely not a plane. So instead, what we're going to do is that we're going to use the LiDAR to produce an estimate of the ground height. We're going to do this with a small, super fast neural net. And then we're going to use these ground estimates to reproject or extract the features from the camera images. And then once we reproject this, basically we will employ this information, whether it is the reprojections or the features themselves. We can use a neural net here also as well to fuse with the LiDAR information and obtain the lane boundaries. And this approach works super, super well. So this is an example of what we did in the past at the VTG. And in this case, we were able to drive hundreds of kilometers with no interventions on highways by using this approach, with no requirement of having any high definition maps in areas you have never seen before, that you have never driven at an outside. And here you see in 3D, this is the ground truth and this is the prediction. And as you can see, we can predict all the different lanes super, super accurately. Right, so this is a truck. Some of the images that you see here, so we didn't see on the back. You have a trailer, and this is what we are basically seeing from. This is without accumulation over time. Since you have typically a very precise odometry or pulse, you can also accumulate this evidence over time and then be more and more robust. But this is not what is shown in the video. In the video, it's independent estimates per frame. So not only is accurate in the image space, it's also accurate in 3D assist. And you can handle changes of topologies. Cool. We've seen other approaches to recently to do mapping. And where these maps, so one way that we've seen this is, for example, from some of these works like Lift, Splash, and Shoot, where the idea is that we want to use camera imagery all around the car. In this case, to basically try to map as we drive. And the idea is that we're going to fuse the information from all these different views to create this bird's eye view map. And in this case, it's going to be of a segmentation type of map. Okay? And contains basically some of the map elements that we might be interested in. Okay, so in the first stage of this model, then each image is going to be lifted from a local two-dimensional coordinate system to a three-dimensional frame that is sort of shared across all the cameras. And this is done by predicting a depth for every pixel. And then in the splatter stage, they employ in particular a point pillars type of architecture that is used to convert the large point cloud from the lifted step to a two-dimensional bird's eye view segmentation of the scene that basically can contain things like the lanes or the drivable area. Okay, so let's look at how this works actually in practice. So this is shown projected into the image as well as in bird's eye view, and you see that you can do a pretty reasonable job at estimating where some of the semantic information is. Okay. In our case, one of the things that we look at is very, very important is that if you think of the task of mapping, the task of mapping is a means to a different end. Right? You need to do online mapping to drive well. So what we look at, in particular with MP3, which is it's one of the best paper award finalists for this upcoming CVPR 21 conference. So what we look in this paper was, can we learn better representations by basically learning the maps such that we drive well? So basically, it's gonna be a neural motion planner. So it's end to end from the sensors all the way to the driving commands. But as intermediate representations, we're gonna obtain these online maps. Okay, so but as I said, it's trained end to end so that we drive well. And this is a very powerful approach where it enables you to create maps that, in particular, are good for driving, because not every mistake is equally harmful. And if you just try to estimate, maps regardless of driving, you will actually see this kind of problem, where you might make mistakes where they're very costly. However, if you train the system end to end this way, you will not have this problem. So in this particular work, we look at estimated drivable area, intersections, reachable lanes, which are the lanes that, given our current location in the lane, that we can actually reach that is allowed by the traffic rules. And this is something that we need to learn, since we don't have a map. We also look at the orientation. And then we look at also dynamic things of the environment, like occupancy, and how the different actors will move into the future. Okay, so let me show you this video. And in this case, I'm going to, on the left-hand side is more of the mapping elements. And the thing that you can see is reachable lanes in blue, as well as the predicted route of giving a command that is like a Google Map type of command, or turn right on the next intersection, right? So it's actually routing. And on the right-hand side, you see the occupancy as well as the estimation of prediction into the future of how the actors are going to be moving with just different colors. And then you see the self-driving vehicle driving the grand truth is shown in black, and what our system actually does is shown in blue here, as well as the predicted plans. And this is a closed loop simulator, meaning that here we are actually driving without the map in this, in this closed loop simulator that has sensor simulation, which we'll be talking about this in some of the other workshops during this conference. Lastly, I want to touch upon a little bit construction. And in particular, in Toronto, we see that there's two seasons. There is the winter season, right, that unfortunately lasts a lot in Canada, and there is the construction season, where basically in the summer, everybody's trying to repair it. And these are basically images that I captured with my iPhone as I was walking to the office, pre-pandemic, in a 10-minute commute. And you see the variety of different situations that you will see in the world. So dealing with construction is actually really fun. Now let's look at what are the types of approaches that people use for construction. Some folks use detection in order to estimate where the elements are. In the past, we use segmentation-based approaches, and in particular, we use memory and our favorite graph neural networks, such that we can actually have a consistent estimate across time as we drive around the construction site. And let me show you this with a video. So what you're showing here is we're going to use LiDAR as well as images. And we're going to use semantic information on the LiDAR as well as the images. And you see as we drive, we get more and more confident, and we can estimate the construction as well as the signage super precise in 3D. And we can estimate the small cones. We see them for the first time typically 150 to 200 meters away from where we are. Very precisely in three-dimensional space, which is sort of remarkable here. All right, so last piece of today's talk is going to be about how to use multi-agent routing for routing these vehicles in order to capture the data to create these high-definition maps. Right, so in order to create these high-definition maps, right, we first need to send out a fleet of vehicles to collect the data, right? So this task can be expensive when covering exceptionally large regions, and we can definitely benefit immensely if we have a sophisticated way to do this routing. So this motivates, the need for systems that are able to autonomously map a region and coordinate an increasingly large fleet of vehicles in an efficient, scalable, and adaptable manner. And I say adaptable because we don't really know how many passes we need for every area. It's as we are building the map that we discover that, we need to recollect because maybe there was too much occlusion or something happened to my sensor. Okay? The question is, can we create such a system? Let's review a little bit of the literature of how people actually do this. So we are basically presented with the following task, right? Given an input of an operation domain and a graph that represents the road that we wish to traverse, the idea is that how can we produce an optimized set of routes for the fleet of vehicles to traverse such that we can create our high-definition maps? Right, so can we autonomously and scalably create and update high-definition maps for these large regions? Now, the idea of an agent or fleet coordination system is not a new one. A similar idea has been exploited in the case of the traveling salesman's problem. In this problem, right, we have a series of points on a plane, and the idea is for the agent or the salesman to visit all of the points exactly once in the most efficient manner, and then return to the original starting position. The vehicle routing problem, right, is a natural extension of this to multiple agents. And given a set of a fixed set of agents, which all start from the same initial starting point, and are expected to visit the same subset of points, so that we say that after all agents have finished, every point has to be visited at least once. That's sort of like what we're after with this type of problem. And bringing back to the mapping problem, right? It's not could be a representation of cities that we need to visit or the individual streets, etc. So one class of solutions utilized for this fall under the designation of traditional optimization algorithms. And these solvers are able to consistently determine the exact optimal solution to relatively large problems, and for example, C with Concord or EKH3. However, they scale poorly relatively to the size of the problem, and therefore tend to be used offline. So in industry, they will run this, they decide the route, the vehicles go, come back home, oh, we have problems, we will need to send them again, etc. Right? So this is a very time-consuming and a very expensive process. So when such solvers are used for large-scale mapping, the initial trajectory is calculated using an iterative solver offline. And basically, the fleet of vehicles is sent out to perform the mapping task, as is seen in this mapping attempt here, so in the number 1 here. However, if there are any mapping failures, then the solution has to be recomputed so that we can actually map the areas where we weren't able to map before. So this is attempt 2 and attempt 3, and then we continue like this until we basically map everything. So this is actually not good. But this is really what is used in industry. Now, in the deep learning field, a few steps have been made towards developing more adaptable solutions. Value iteration networks, such as the generalized value iteration network, are able to explore the environment in a learnable manner, but they struggle to perform long-term planning. Graph attention networks, types of solutions, are able to focus on a specific sets of nodes within a complex graph, and therefore enable more sophisticated planning and information passing. It should be noted that, however, that all deep learning networks do not have the same guarantees as traditional solvers and can require expensive large-scale training to be used really effectively. Now let's look at some of the work that we have done in this area to really get a scalable sort of routing of vehicle fleets. So the overall graph attention network flow here generally operates in the following way, where we extract node information from the map graph, encoding everything that we know about what we have observed so far, and then we send these node encodings into some in the form of some internal node-based graph attention model. And this model basically iteratively exchanges information between each of the nodes and allows for complex planning to occur in a distributed manner. Now, some form of communication model exchanges node information between each of the agents and allow the relevant discoveries made by each agent to be shared across the different, the entire fleet. And this final output is then returned to the map graph in the form of a per node value function that's going to be used in order to decide where to go next. Okay? So this is a very flexible and very dynamic way that can handle things like dynamic routing because of traffic, because of error, etc. All right, so let's look at how this works in practice. So here we showcase our approach, which we call Marvin, which is an attention-based graph neural network, which is able to dynamically coordinate a fleet of vehicles as a swarm in an online setting. So we see 2 attention heat maps produced by Marvin, visualizing besides each other, which comes from 2 different vehicles within the fleet of vehicles that we are routing. The red dots represent the current position of the agent in each scene. I notice that the agent's strategy alternates between focusing on a small set of nearby regions and discovering new regions to travel for exploration. The agents will dynamically reroute themselves until the mapping task is basically complete. We also want to qualitatively compare the mapping process of Marvin to another competitive architecture, in this case, the generalized value iteration network. And we show that Marvin really results in much faster routing, particularly better exploration. And due to the mapping failures that can occur, right, and the lack of information about where these failures are going to be a priori, this is the way to really ensure the completeness of the graph. All right, so we're going to compare the qualitative so we're going to look at the visualization of mapping, right? As in this case, it's going to route a fleet of 20 agents. And in a small region around Chicago, we can do this at the full Chicago scale. But here, for visualization, let's look at just a relatively small area. And we can see how the agents begin at a single point in the map, and they're able to coordinate online to really spread out and map the entire area that we are actually interested in. Spread this once again. And as they expand, they also are able to adapt the mapping failures that occur by sending messages to other vehicles, and potentially other vehicles might be remapping, or even the vehicle itself. Now, finally, the agents, as the agents finishes each of their subregions, they're able to independently return to the original starting location, which typically might be the charging station, if hopefully their vehicles are electric, which we hope they will be in the future. All right, so to conclude, we discussed today two types of maps, right? The rough topological maps, as well as these super precise high definition maps. We look at how to build the geometry, as well as the semantics for high definition maps. And we discussed potential ways to do this process offline, as well as online, which is required for safety. And finally, we look at how we can employ cooperative multi-agent systems or methods in order to be able to route a fleet of vehicles into where they should be driving, such that we can collect and build maps in a single data collection process. So this is all for me today. Thank you for your attention.
Thanks very much, Raquel, for your presentation. And also thank you very much for present here. We have a bunch of questions. Maybe we can start with the question online. So first question from Ross. He's asking, like, for the crosswalk and boundary raw data collection, is that done by UAV?
Yeah, in the results I show you in today's tutorial, the collection was done by a fleet of vehicles driving around the environment using SLAM-like systems in order to put all that into correspondence, and in particular LiDAR-based system. Then once you have that into a three-dimensional geometry map, we basically render from the top the representation of those maps where we have removed the moving objects. And we use also, we build panoramas of the ground by exploiting the cameras. And then given that input representation, then basically we extract the boundaries as well as the crosswalks. Now, if you think about, so this is what we did in this particular work. Now, if you think about, the input representation, you can basically, instead of having those images that are like LiDAR plus the panorama, you can just replace that by aerial images or images captured by drones, etc. So I mentioned that in a tutorial because I think it's an avenue of very interesting work that should happen one of these days.
Okay, thank you. The second question is from your work for the deep multi-sensor lane detection prediction, how far distance it can predict up to?
Sorry, I couldn't hear the beginning of the question. Do you mind repeating that? I'm really sorry.
There's a work presented for the deep multi-sensor lane detection, and the question is how far distance could it predict?
Yeah, fantastic question. So this really depends on the sensors that you utilize. In that particular paper, we, for the results, we use 50 meters in front of the vehicle, and we use in front and not all around because we were using trucks, and they basically have a trailer which you cannot instrument any sensors to see, on the back. Now the approach is, is general. So if you have access to far range LiDAR, as you can, there is new sensors now that can go all the way to 300 meters. And if you have cameras that actually have high resolution, you can actually expand the range that you see much farther. So yeah, it's just a function of your, what your sensors are. But typically with a Velodan 64 which will be sort of like previous generation sensors, what you will see in Kitty. More than 50, 60, 70 meters you don't really see on the ground. And then the network will need to really extrapolate beyond that in order to have an estimate of the ground, and you will need to fuse earlier with the images in order to basically do depth from monocular or multi-cameras if you have multi-cameras on your platform.
Thank you. And another question is, how sensitive is the predicted model or prediction model for the weather conditions? For example, foggy, rainy, or any other weather conditions?
Let's see, I show so many models, so I wonder which one are we talking about here. Let's assume it's the same one as we are just talking now. So it's actually not very sensitive. And we employ this technique to drive around highways for hundreds of kilometers with no intervention, 3 years ago, something like this, while working at Urtasun. And this was a really in production, meaning that it has to deal with all different conditions. Now, we didn't really test it in super mega heavy rain, which one of the things that will happen is that your LiDAR measurements will get like super noisy, so you need to be a bit careful. Or we didn't test it in rain, since we were driving this, in Arizona in I-40. But good question. I think one of the things of that's interesting of doing trucks now in Canada is that we're going to have plenty of data of bad weather conditions to actually answer quantitative your question maybe in next year's tutorial, assuming there is one.
Great. That's all the questions from online. Is anyone having any questions from the audience? You can just unmute yourself. Or if you cannot, ask me to help you unmute yourself.
There is a hand raised. I don't know if that's a question, I'm assuming.
Yep, let me see. Okay. I think you're unmuted. It's a Sida.
Yeah.
Go ahead.
So you were saying, so for this model, so do you need suppose if there are images that are like the resolutions is like very bad, then what do you do in those situations? Do you super isolate, or do you use any kind of image enhancement techniques, or is it bad for deep learning?
Good question, Sida. Nice to meet you. Let's see. So we don't use super resolution or anything like this. First of all, because the cameras we employed had enough resolution for the task at hand. I mean, you can try to do that as a function of extra supervision. Now, typically for the tasks that you're interested in here, and given the types of cameras that we use in automotive, it's really not necessary to do things like super resolution. But if you put a super mega chip camera that has 300 pixels, maybe something like event cameras or things like this you might be interested in using, then maybe you need to do something like this. Yeah, interesting question. We haven't, we didn't need to do anything like that.
Thank you.
Thanks. Any other questions? From anyone?
All right. Thank you. Oh.
Okay. Thank you very much, Raquel, for your presentation. And we'll have the next speaker up. So our next speaker will be not presenting today, but they sent me a pre-recorded video because this is the nighttime for them. But I'll just help presenting that or play that video here. So next presenter is Dr. Ruisheng Wang, who's a professor at University of Calgary in Canada. And sorry, I have to share my screen. Just a sec. Okay, can everyone see my screen?
Yes.
Okay, sounds good. So Dr. Ruisheng Wang is going to present his work on mapping from LiDAR point clouds and images.
Thank you very much for having me at this tutorial. Welcome everyone to my presentation on mapping from LiDAR point clouds and images. This is a joint work with a bunch of collaborators, my postdoc Lily, PhD student Perpetual, and Akshay. Our goal is to integrate multimodal data for automatic creation 3D maps. Here we focus on LiDAR point clouds and camera images. It's very intuitive to combine LiDAR with images for our mapping purpose. The image contains color and texture, but without three-dimensional information. The LiDAR point cloud contains 3D information, but without color and texture. In order to combine both datasets for mapping, we need to register both datasets. The first work I'm going to present is learning to register aerial images with LiDAR. The registration between LiDAR and image is actually a 2D to 3D matching problem. Traditional methods, especially before deep learning, what people normally did is to transform 2D to 3D matching into 2D to 2D matching by projecting LiDAR into different 2D representations, such as LiDAR intensity image, LiDAR point without intensity, which is actually the occupancy map, LiDAR depth map, which is a distance from the object to the LiDAR sensor. The green color indicates the distance, the further the latter. Here, we overlay LiDAR projections onto the camera images. You can see the color, which is from the camera image. When we project LiDAR 3D point clouds into 2D representations, we actually have the association between the LiDAR projection and 3D LiDAR point clouds. If we establish the correspondence between camera images and LiDAR 2D representation, which means we already established the correspondence between camera images and LiDAR 3D point clouds. There are three categories of methods for 2D to 2D matching based on handcrafted features. The first one is key point-based matching. Basically, it uses safe or serve to extract key point, then matching the key point. Instead of matching the key point, structural feature-based matching is to match connected segments. The last category is intensity-based matching. Instead of extracting any features, intensity-based matching is to compute mutual information from entire intensity value from the images, then maximizing mutual information to estimate the transformation parameters. Recently, the learned descriptors have outperformed handcrafted ones, such as safe serve, fat point feature histogram, and short. However, there is no publicly available dataset for registration of aerial images and LiDAR. The deep learning-based methods needs a large dataset containing 2D to 3D correspondence to train. Another issue is association between 2D and 3D descriptors is challenge. There is a large discrepancy between 2D and 3D representations. In this work, we first create a training dataset. We use SPRS Toronto dataset to create 14,000 2D to 3D correspondence pairs. This dataset is from Photogrammetry Society. It contains aerial images and LiDAR with pulse information covering the same area in the downtown of Toronto. We extract 3D patches from the LiDAR point clouds. Based on the pulse information of the aerial camera, we can back project to the aerial images to find the 2D patches. In this way, we can automatically create 14,000 2D to 3D correspondence pairs. The key of the network is to map 2D and 3D features into a shared space with a close attention module to exploit the intermodality relationship and complement each other for 2D to 3D matching. The network architecture consists of 3 branches. The first is a CNN-based 2D output encoder. The second is a point light-based 3D output encoder. The input image and the point cloud data is reconstructed with the photometric loss and the CFR loss, respectively. In the middle is a close attention module. We use image features to weight point cloud features and use point cloud features to weight image features. The similarity between the 2D embedding and the 3D embedding is further regularized by a triplet loss. The total loss will be the summation of these 3 losses. Here are some experimental results. The blue cross indicate the LiDAR point clouds. We compare our method with the LCD paper, which was published last year in AAAI. Our method with close attention achieve improvement in terms of top 1 to top 7 error. Next, I'm going to talk about semantic segmentation-based targetless calibration, which is to estimate 6 degrees of freedom rigid body transformation between LiDAR and the camera. Calibration is an old problem. Traditional methods use calibration board in a lab environment for the calibration, and it cannot be adapted to decalibration during the operation. User-defined methods to extract features such as edges and corners from LiDAR point cloud and camera images use computationally expensive RunSec to estimate parameters, and it lacks robustness. The hybrid methods use a pre-trained model for semantic segmentation of images and point clouds. Based on the segmentation, this method estimates the transformation parameters, followed by a cost function refinement. The problem is this method needs multiple pairs of images and point clouds to get a cost estimation. The deep learning-based method use images and point clouds as the input. The output is a 6 degree freedom rigid body transformation parameters between LiDAR and camera. The problem is this method assumes that an initial cost transformation is already available. Based on above observations, you can see most of current methods only use selected information for the calibration. For example, only depth is used for online calibration, and the intensity returns from the LiDAR are ignored. Second, current deep learning-based methods address just the online calibration and cannot be used for complete calibration. Further, the methods don't meet expected accuracy and still have significant errors. The calibration overview. The total rigid body transformation can be written as the fan transformation times the coarse transformation. In the calibration, we can have a 2-step approach. The first step, we estimate a coarse transformation, then we can estimate fan transformation. Finally, we can get the accurate transformation metrics for the calibration. This is an overview of the coarse calibration. We use pre-trained networks for semantic segmentation. For image, we use DeepLab Bridge 3. For point cloud, we use Cinder 3D. And after the segmentation, we estimate the centroid for each object in a class using k-mean clustering, then followed by transform estimator and transform selector for estimating coarse calibration parameters. The transform estimator. For the calibration, the point cloud need to be matched to the image. Since the number of features in the point clouds are normally more than that in the images, there are unknown correspondences between the features of the segmented point clouds and segmented image. Therefore, this is similar to a blind PNP problem. However, we know the correspondence of segmented classes in the images and the point clouds. For instance, the centroid of the cars in a point cloud must match the cars in the image. Therefore, this becomes a semi-blind PNP problem. Since class correspondences are known and the correspondence of the objects in the semantic class are unknown, there exists some permutation of the feature objects that are in the right combination. Therefore, the permutation generator generates different permutations of the objects within the class. The PNP solver estimates the transformation for each of these combination of correspondences, and a major of them can be filtered out using a priori. For example, the LiDAR and the camera are not more than 2 meters apart in all the axes, therefore limiting translation vector within 2 meters. After filtering out false correspondences using the priori, for the very few possible combinations remaining, the loss function is used to get the best estimate. Here, we use photometric loss and Manhattan distance loss for the estimate. The Manhattan distance is the distance from the centroid of each class in the point cloud projected onto the image plane to the centroid of each class in the segmented image. The total score for each transform is the summation of all the costs. For the photometric loss, the label of the projected point cloud is compared with the surrounding labels of the segmented image. We use the 3x3 kernel of labels for the comparison. We only penalize the incorrect matchings, which means if the point cloud label is not same as the image label, the score will be 1. The score kernel will be average number from this kernel. The total score from this image will be the scores from all the kernels. The objective of the fan transformation is to train a neural network to predict the transformation between point clouds and the images. To estimate the fan transformation between point clouds and the camera images, we use VesNet as a backbone network for extracting feature maps from the images. The average pooling layer and the final fully connected layer are removed from the original network to give us the feature maps for images. Similarly, another REST network is used for the depth and intensity images. The feature maps from both the networks are concatenated and passed onto the feature extractor network. The feature extractor network consists of 3 layers, with each layer containing a 2D 3x3 convolutional layer, followed by patch normalization and relu activation function. The output of the feature extractor is passed onto regressor network. The regressor network has 2 branches, one for rotations and another for translation. the rotational regression network produces 1x4 vector representing quaternions. The translational network is similar to the rotational regressor networks and produces a 1x3 vector that represents x, y, z values. There are 3 loss functions for the fine calibration. We have a target transformation and apply to the raw point cloud, which will be used as a target point cloud. The predicted transformation from network is applied to the raw point cloud to obtain predicted point clouds. Since the point-to-point correspondences are known, the 3D Manhattan distance for each point is calculated, and the mean Manhattan distance is used as a loss function. Similarly, for rotation loss and translation loss, we have the Frobenius norm and L2 norm to minimize the errors in rotation and translation. This is an experimental result. This picture left shows the original images. The right is segmented images. This is the left is the original point cloud. The right is a segmented point cloud with the centroid computed from k-mean clustering. This is a result from the coarse calibration. You can see the LiDAR point and the images is approximately aligned. This is a result from fine calibration. The top row is miscalibration between camera and the LiDAR. The middle row shows calibration estimated from our network. The last row is the ground truth calibration. After LiDAR point cloud is registered with camera images, we can use both LiDAR and camera images for semantic segmentation. Here, I want to talk about fusion of aerial LiDAR with hyperspectral images for 3D labeling in the aerial LiDAR point clouds. So what are hyperspectral images? Hyperspectral images have very high spectral resolution. Because of very high spectral resolution, it can optimally distinguish very fine classes, which are spectrally identical classes. It lacks three-dimensional information, therefore it's poor to suboptimal distinction between geometrically identical classes. For the comparison, I want to talk about multispectral images. Multispectral images have limited spectral information. The discrimination of very fine object classes is suboptimal. It also lacks three-dimensional information, therefore it's poor to suboptimal distinction between geometrically identical classes. If you look at the LiDAR point clouds lacks or have limited spectral information, therefore it's poor to suboptimal distinction between very fine object classes. But LiDAR point clouds have high spatial resolution with three-dimensional geometrical information, therefore it can better distinguish geometrically identical classes. The high spatial resolution also means redundancy. Current dimensionality reduction methods have problems differentiating spectrally similar objects. This is because most existing methods are based on low correlation or high variation data without considering relationships between object classes and spectral bands. Therefore, some high correlation bands that can separate two or more spectrally similar classes become statistically insignificant, thus get replaced by other high variation information. However, optimizing the interclass spectral variation and the intra-class similarity will boost representation accuracy. In this work, we propose a class-aware band selection and reduction methods which address this problem. Optimal feature representation of multimodal data is a challenge. This is because similar properties may exist in different object classes, and variations may exist in the same object classes. Second, most existing LiDAR and hyperspectral imaging integrated methods are either based on CNN or handcrafted features and user-defined constraints. We use a double-branched convolutional Gaussian-Blurry deep belief network, in short CGBDBN, for semantic feature extraction. Optimal feature representation of multimodal data is challenging. This is because similar properties may exist in different object classes, and variations may exist in the same object classes. Second, most existing LiDAR and hyperspectral imaging integrated methods are either based on CNN or handcrafted features and user-defined constraints. In this work, we use a double-branch convolutional Gaussian-Blurry deep belief network for semantic feature extraction. Why CGBDBN? First, CNN is a strong discriminator model, but DBN is a strong generative model. Thus, the proposed CGBDBN is a comprehensive model. Second, the CGBDBN inherits the weight sharing and translation invariance properties of CNN, and DBN renders the model filters generatively, thus allowing a more effective semantic discrimination. The CGBDBN model is faster than the CNN with standard backpropagation. This is because we use a second-order stochastic dialog Lambert-Marquardt backpropagation for computing the fittest learning rate per epoch for a faster convergence. The method overview: 3D point clouds can be converted to images, but simply doing so will result in the generation of hash images and a great loss of other geometrical information. So a few generic LiDAR-based features are extracted and converted to images to serve as input to the deep learning model. Since hyperspectral images are high-dimensional with redundant information, we design a dimensionality reduction method, CBSR, which maximizes the inter-class variation and minimizes the intra-class similarity of the hyperspectral images to obtain a more discriminative representations. I will talk about CBSR in the next slides. The extracted LiDAR-based features and the output of the CBSR are individually fed as input into the double-branched CGBDBN, the result of which are then fused and classified to obtain predictions of the experimental data. The proposed dimensionality reduction method is called class band selection and reduction. Most hyperspectral dimensionality reduction methods are either based on band selection or band feature extraction. The CBSR combines both methods by iteratively selecting class-aware high-variance spectral bands, then grouping the selected bands using cross-entropy and structural similarity indexes, and variational Bayesian Gaussian mixture model as a clustering method. Since the members of each band group are of similar characteristics, reducing the dimensions of each band group will result in minimal loss of crucial information compared to direct reducing the dimensions. Therefore, the dimension of each band group was reduced to the first N component that cover 99% of the total variance in that group using principal component analysis. The principal components from all band groups are then concatenated together as the final spectral representation of the hyperspectral image. Thus, CBSR maximizes the inter-class variations and minimize the intra-class similarity of the query hyperspectral image to obtain a more discriminative representation. Now I will talk about a convolutional Gaussian Booley deep belief network. The CGBD-BN is used for deep feature extraction, and per its name, you can see it has two branches. One takes the generic LiDAR-based features as input, and the other branch takes the reduced hyperspectral image representations. As can be seen, the CGBD-BN is a stack of convolutional Gaussian Booley restricted Boltzmann machines, where feature maps are propagated from layer to the next. The CGBD-BN is probabilistic, bipartite, and bidirectional, hence generative in nature. From the left figure, you can see SW by SW convolutional filters are applied to zero-padded SV by SV input images to produce SH by SH by M feature maps. This ensures the reconstructed images will be equal to the input size. On the right, mathematically, the equation 1 represents the energy function that needs to be minimized. To do that, the joint probability distribution on equation 2 needs to be computed. Using Gibbs sampling, conditional probabilities of the visible and hidden units are computed as equation 3 and equation 4. To prevent Gibbs sampling from being infinite, the K-step contrastive divergence learning algorithm is used to estimate gradient of parameters like weight, bias, momenta, etc., and update them so as to minimize the object function, which is a reconstruction error. After we got deep features for LiDAR and hyperspectral images, how do we fuse them for classification? There are many ways of building and enhancing stacked ensemble models. For example, use different training algorithms, hyperparameter settings, feature subsets, or training set. Here, we use the same training algorithm, random forest, with different hyperparameter setting and feature subset per model. And the data fusion is by probability averaging followed by differential weighting. For the experiment, we use IEEE GRSS 2018 data fusion contest, especially the Houston dataset. It contains multispectral LiDAR and hyperspectral images with 48 bands. In this dataset, there are 20 highly unbalanced urban classes, such as healthy grass and stressed grass, and artificial turf and evergreen trees. For roads, it has roads, highways, crosswalk, sidewalk, parking lot, railways, unpaved parking lot. Those are spectrally similar objects. This is the experimental result. The last column is the result from our proposed method. The proposed method achieved the best outcome on all per class and overall performance. The proposed method combines the reconstructive ability of the DBNs with spatial neighborhood context provided by CNN to generate highly discriminative, high-level hierarchical semantic features towards classification. Second, the developed CBSR method can distinguish spectrally similar classes. The proposed method was able to better distinguish road type classes, such as bare earth, paved and unpaved parking lots, railways, and stadium seats. Third, the stacked classifier combines the advantages of two classifiers to produce optimal result rather than a single classifier. This is some visual results from the comparison with existing methods. We also compare with our methods with deep learning-based methods, especially CNN-based methods and non-deep learning-based methods. For some reasons, we have to use another dataset called golf course dataset. In this dataset, there is no LiDAR data provided. Instead, there is a digital surface model, DSM, plus an intensity image and hyperspectral image with 64 bands. There are 11 urban classes in this dataset. Because of limited LiDAR accuracy, we achieved less accurate results on sidewalk and yellow curve classes. However, we achieved the best result in terms of overall accuracy, which is 93.62. This is a result from labeled point clouds. The bottom row is input point clouds. The above row shows labeled point clouds. The different colors indicate different object classes as listed in the bottom row. Because we use hyperspectral information, it opens an avenue to label point data into subclasses. For instance, we can label deciduous and evergreen trees. We also can differentiate artificial turf, stressed grass, healthy grass. We can differentiate roads, highways, major thoroughfares, etc. This is a result from labeled point clouds. The bottom row is input point cloud, and the above row shows labeled point clouds. Different color indicate different objects as listed in the bottom. Because we use hyperspectral information, we can label point clouds into subclasses. For instance, deciduous and evergreen trees, artificial turf, stressed grass, healthy grass. For roads, we can label to highways, major thoroughfares, roads, etc. Another scenario to use images for mapping is texture mapping. Before text mapping, the multiple images must be in consistent color. Here, I want to talk about color corrections before the texture mapping. There are photometric inconsistency between multiple images. This is because these images may be taken by different cameras under different lighting conditions. So we need to optimize color inconsistency for multiple images before texture mapping. Traditional methods for color correction, the first one is path propagation. This method needs to select one image as a reference image and transfer color of target images into it. The problem is this method will have large accumulated errors. The second is a global optimization. This method corrects images simultaneously rather than sequentially, and it uses same color mapping function for all pixels in an image. The problem is the ability to correct local color discrepancy is low. To address this problem, we propose a joint optimization method that consider global and local color consistency. We first apply superpixel to the input images. And for each superpixel, we will use different linear models to correct local color differences. To globally solve the model parameters for all images at the same time, during the model parameter optimization stage, we design a special cost function that considers both gradient preservation and color consistency. Finally, we got the corrected images. This is a linear color correction model. This is the objective function, the data term, which is defined as the sum of the squared differences of the corrected colors between all overlapped superpixels, is applied to evaluate the color consistency between images. We design a smoothness term to constrain the linear model's smoothness and assume that the linear models of neighboring superpixels in the same image should be similar. The regular term ensures that the solution is valid. Here, we assume that the corrected image colors should be as close as possible to the original image colors. The corrected image may suffer from the problem of over-blurring, which will destroy the original image details and lower the sharpness of the object edges. We design a gradient term in our energy function to preserve the image gradient and avoid the loss of image details. The global linear model is a virtual model. It is only applied to constrain the proposed local color models, and it will not be applied to correct the color for input images. We attempt to constrain the parameters of the local linear models in one image to be close to the parameters of the global model. The energy function is a quadratic objective function, which can be easily solved in a closest form by setting the derivative to 0. This slide shows how gradient terms affect the color correction. The lambda is a coefficient for the gradient term. If the lambda is 10, the image will get sharpened. If lambda is 0, which means we don't have the gradient term, the image gets blurry. This slide shows how global terms affect the color correction. The left is a self-composite image. The middle is a result from the color correction without global constraint, and the right column shows the result with global constraint. With the global term, we can see the color is consistent over all the images. We conducted our experiments on 5 datasets captured by different sensors from different areas, including 3 satellite datasets, 1 UAV dataset, and 1 panchromatic image dataset. The land, coast, and city dataset consists of multi-temporal satellite images. In this dataset, there are severe color differences between the original images. The village dataset is comprised of hundreds of images captured by a UAV camera. The kitchen dataset consists of a series of images acquired for 360 panchromatic image production. And the evaluation metric consists of the color distance, which is applied to evaluate the color difference between overlapped corrected images, and the gradient loss, which is applied to evaluate the gradient variations between input images and corrected images. Smaller values of the color distance and the gradient loss indicate a higher quality color correction result. We can see that our approach offers the best CD scores for all datasets, and these scores are better than the scores of the rest of the 4 approaches, especially for the city dataset. Our approach offers the best CD and GL scores. However, for coast, village, and kitchen datasets, we found that the GL scores offered by our approaches are not the best. The main reason is that the color information of the input images in this dataset has been greatly changed to eliminate the severe color differences, and some gradient information is sacrificed. Although Xiong and Puli's paper offers the best GL scores for these 3 datasets, the CD scores of this approach are the worst. Considering the CD and GL scores together, our approach outperforms the rest of the compared approaches. This is the visualization of our result. The left is the input images, the right is the result from our methods on codes dataset. This is the result from Wang and Low's method and Xiaofeng and Police method. This is the result from Sun and Yu for the color correction on the codes dataset. This is a village dataset, the original input images. You can see there are severe color difference between the images. This is a result from our method showing the color is consistent. After the color corrections, the images can be used for text mapping. Text mapping is to map images onto the 3D models that generated either from LiDAR point clouds or camera images. Text mapping is to map texture onto 3D models. The 3D models can be small objects, also can be large-scale urban scene. After text mapping, we can create 3D photorealistic models. To do text mapping, we need to load the camera position with respect to the 3D models, which is a 2D to 3D registration problem. After we load the images location with respect to the 3D models, we need to select best view of images for the texture mapping. However, there are geometric misalignment. Look at these three pictures. You can see the misalignment between the texture and the models. The main reasons are the accuracy of 2D to 3D registration is limited. Second, the geometrical accuracy of the 3D model is also limited. These two reasons cause the misalignment during the texture mapping. Our method in the step 1, we do the camera pose optimization to eliminate the error of the initial pose, which is improve the 2D to 3D registration. For each vertex color, we back project onto the multiple images. If the pose is correct, the color should be the same. So we solve this objective function through minimize the color difference. We can estimate the camera pose. This slide shows the camera pose optimization process, and the left image is the input texture model. After the optimization, we can see the misalignment get improved after 30 iterations and 50 iterations. The second step is view selection. We need to select best view for each mesh. We need to select the best view from multiple images for each mesh in the model. We solve this using graph cuts. The last step is local optimization to eliminate local geometrical error. There still exists geometrical errors after camera pose optimization because of limited accuracy of 3D models. In local optimization, we correct the coordinates of the texture to eliminate the local errors. You can see the result before optimization and after optimization, the misalignment gets improved. These are more results from our method. And the left is the multi-view images. In the middle is a dense matching generated mesh. The last images is a result from texture mapping. Here we have more results from the 3D models generated from LiDAR point clouds. We compare our methods with open source software, OpenMVS, and our result gives better performance. We also compare our methods with some commercial software, PhotoScan. this result shows our methods achieved better texture mapping. And this is another comparison with commercial software context capture. And our methods achieved good result. Thank you for your attention, and I also want to thank my research sponsors.
Okay, thanks very much for Dr. Ruisheng Wang's presentation. Not sure if anyone have any questions so that I can pass on for Dr. Wang. Don't see a raised hand. That means there's no question from the audience. Okay, thanks everyone. We'll have a break from now to 3:30 p.m. and then we'll have the next presenter up at 3:30. Thank you very much. We'll stop recording and then we'll see you in about 20 minutes.
Good afternoon, everyone. My name is Ben Kadlik. Welcome to this Vision Meets Mapping workshop at CVPR. Today, I'm going to talk about some work we're doing at Amazon around computer vision, using computer vision for location-based reasoning and mapping. A quick confidentiality request before beginning, although this being a virtually recorded presentation, likely not to be as big of an issue. But here's a brief overview of what I'm going to cover in my talk today. I'm first just going to give a brief overview of some of the robotics work happening at Amazon. I'm next going to go into our use of maps and a specific use case of maps and why it's important. And then finally, describe some challenges and talk about Vision's role in mapping for robotics at Amazon. Brief introduction to myself. I guess I've presented at this workshop in the past. I'm a manager of the perception team here at Robotics AI at Amazon, and my team's responsible for developing localization, mapping, and obstacle detection capabilities for our autonomous mobile robots. Prior to Amazon, I was working on AV Maps in Uber's ATG group, and then some time before that, working on ride sharing at Uber, as well as the Bing Maps product at Microsoft. So a little overview of robotics at Amazon. Hopefully what this slide gives you a sense of is that there's a lot of different robotics efforts happening at Amazon. Some of the different organizations and groups are highlighted in this slide here. So you can see, started from the upper left, a group called Robotics AI, of which my organization, which is called Canvas, is a part of. This is what I'll be focusing on for most of the presentation today, is talking about this Canvas work we're doing. There's also the Prime Air organization, where they work on drone technologies. There's the group called Amazon Robotics, which was formerly known as Kiva Systems, as a group called Scout that builds a sidewalk delivery robot. And there's actually a lot of other areas across Amazon, such as in AWS and others, where robotics are happening. A little bit about the robotics group I'm in. Our mission is to enable robots to interact safely and fluently with our fulfillment centers at Amazon. And we're developing some AI solutions that allow robots to learn from their own experiences, learn from each other, and learn from the people around them to build AI that helps feed itself. And I'll probably be talking a little bit less about AI today, since this is going to be a mapping focused presentation, but I am going to spend some time talking about sort of how we use computer vision in mapping, but maybe the first thing I'll sort of talk about is this question here. Why do we need maps at all? And this partially gets into how do we use mapping technologies for our robotics problems at Amazon. So keeping it pretty high level here, there's two primary use cases. The first is being able to localize our robots inside of these large facilities where we operate. That's what this video on the left is describing. You see a couple robots in green moving around this large map of a fulfillment center that we're slowly zooming out to show you. And then on the right here, you show a video of the importance of obstacle locations for planning. Maybe not the best video to describe this approach. I'll show a little bit more about this later. But essentially, as a robot tries to plan through one of these large environments, knowing where there's traversable and non-traversable spaces is really important. Cool. So another thing I want to focus on, since it's a big part of the work my team does, is the types of environments we operate in. And specifically, I want you to be thinking about the challenges of these environments when you're using computer vision based approaches for things like localization and obstacle detection and planning, which is the focus of my team's work. So this next video here, let me see if this slide will play. Okay, here it goes. Yeah, I love this video. This is a fulfillment center where our robots are operating today. You'll see some, it's going very fast intentionally. You'll see some robots. I'm kind of showing my cursor around some of them here, helping move materials in this environment. But what I really wanted this video to portray to everyone is just how dynamic these spaces are. We deal with a lot of challenges like visual aliasing, where a lot of places look the same. We also have this challenge where, and you can kind of see it just right in front of the camera here, where if you come back around to a location where you were at previously, so let's say you map some keyframes in this part of the fulfillment center here, you may come back around to it and later find that it looks very different than how it appeared previously. So these are some of the challenges we face in these dynamic environments. Obviously other technologies can be utilized to help with localizing in these environments as well, of which we also use, but we do try and focus our technologies primarily on using computer vision because there's an extensibility benefit to being able to deploy this in lots of different environments with very little infrastructure. So that's been the focus of a lot of what my group does here at Amazon. Next slide, just kind of showing a very high level, kind of a hand-drawn workflow of how computer vision fits into part of the system that we use here. So we work with a stereo sensing system where we're computing dense depth maps. We have a SLAM system that consists of both a front end that updates some poses, as well as a back end that is intended to help with map registrations. And so you can think of a SLAM front end system as producing odometry updates at a certain frequency, say 20 hertz or so, providing those odometry updates to this back end system that has some information about a map and is able to switch to different keyframes in that map in order to register against a global frame. And you can also think of a cart that may be lost or starting up in a new location where it needs to relocalize itself by querying against this map to figure out where it should be. So that's kind of on the localization side of this, but this vision information is also used for generating obstacle detection information, so such as using dense depth maps to identify where there are obstacles in the robot's way, and then placing those down into a map that lets the robot know what's around it. So this next slide here is going to give a little bit of a demonstration of how sort of our mapping technology works. Like I said, this is a vision-based mapping system, and what this demonstration is showing is just a robot driving around. In this case, it's actually in a simulated environment, but you can imagine that obviously this works the same in an unsimulated way. It's just easier to generate a video this way. But as it's driving around, and what it's basically doing is building a map. So it's using visual odometry to sort of determine its position between these two different points in these yellow lines it's drawing, and it's placing keyframes into this map that it's constructing, sort of seen by these little three colored access points. So what's happening now is the robot's sort of completing a loop, and it closes this loop, and you see that it's no longer dropping these keyframes behind it as it moves. And the reason is that it's actually now being attached to a map. So it's come back to a place it's seen before visually, seeing similar features. And with this graphical change made to the videos, you can now see exactly which keyframes the robot is attached to at different points in time. You can see it driving around while connected to that map, and then here it starts to stray off of that map, just to give an example of what it would mean to do another loop closure within an existing map. So now it's creating new odometry frames, creating a new loop closure edge, and then it connects itself back into the map. So this is really just sort of intended to help you all understand how our mapping system works and how it uses computer vision to map out an environment that allows a robot to eventually come back to the same place and place itself in the same location that it was at previously. And hopefully the reasons for why this is important are obvious. Some of the things I would highlight include if this robot needs to get to a very specific pickup and drop off location, if it's going to be picking up some packages or dropping off some packages inside a fulfillment center, it's really important for it to be able to navigate to a precise waypoint in this environment, and using a map is a great way to make that be a reliable operation. So the next slide I'm going to show here is showing just sort of the scale of the problem that we're operating in. So this is a large area of a fulfillment center. This is sort of what we call our cost map visualization initially, the black and the white, and then laid on top of it is our pose graph, or our localization map, depending on how you think of it. And this is an example of a map of just a newly mapped area. So you can pretend our robot just sort of arrived in this area for the first time, similar to the video I was showing you previously. You can imagine it driving around either with the help of a human or autonomously trying to just sort of navigate this space and slowly creating this map, which is the mouse is highlighting over it to show sort of the graph structure that's created as it's going. So you can see these edges formed between paths, and hopefully you can imagine if a robot would come back around to one of these points on the map, you can imagine how it would then be able to localize itself, because it would see some visual information that's stored in this graph and know exactly where it is in this very large environment. Now, after one challenge that we have to deal with a lot here at Amazon is that our robots are operating for very long periods of time. They're seeing the same environment over and over. That environment is changing over time, and we have to somehow allow this map to adapt as this environment's changing, and while there's a continuous use of robots operating in this environment. Let's see, oops, sorry, let me go back. So we end up with this graph that essentially needs to be pruned and reduced over time, because we continue adding information to it as robots observe new things in the environment, and that leads to some challenges. Whereas this pruning can sometimes, removing some of these edges that are shown, which is in a process called pruning, it can actually change the makeup of the map. And yeah, I guess that's a challenge that I'll maybe touch on in a little bit here. Let me see if this video will play here. I guess I missed the lead into slide. So one cool thing about sort of the approach we've taken here to having a vision-based mapping system is that it's really easy to generalize our robotic platform to other applications. And that's sort of what this next video here is going to demonstrate. So since we rely on very little infrastructure, physical sensors, indoor Wi-Fi type of technologies for our robots to operate, it's really easy to deploy them for solutions such as this. So this was a project we did in the early days of COVID. It's called Buzz Lightyear. It's essentially one of our robots with a very large UV array navigating through a Whole Foods and essentially using that very powerful UV light to kill any virus that's left on the shelves of the store after shoppers have come through. So again, this is the same sort of robot that we use inside of our warehouses, operating in where there's humans and aisles and new places, new environments that the robot's never seen before. But the fact that this robot is just using visual features makes it really easy for us to be able to take it into a brand new environment, you know, a grocery store in this case, make some changes to its hardware, which obviously I'm not going to be going into here, and solve some very different problems then that are very impactful for our customers at Amazon. And of course, these days that includes Whole Foods, which is another Amazon company. Cool. So I know this is a recorded presentation I'm making, and it's a little shorter than my time frame, but since it's recorded, I guess I'm not going to have time for the Q&A, but I will direct you to this link here. Amazon is hiring a lot of folks to work on different mapping problems. I know I covered things at a pretty high level in my presentation here today, but hopefully it gives you a sense of some of the work we're doing at Amazon by applying computer vision to mapping problems. If you're interested in jobs, reach out here. And if you're interested in chatting with me in more depth on any of these topics, my information is available in the conference details. So hope you all have a great virtual CVPR this year. Hope to see you all in person at the presentation or at the conference again next year. And we'll see you all later.
Okay, thank you, Xiaofeng. Please start.
Okay, great. Let's just get started. Thank you, Sean, for the invitation, and I'm very pleased that I will tell you more about the computer vision work we're doing at Amap. It's probably fitting that I'm giving the last talk at this tutorial, because I'm sure you've heard a lot about great work and great algorithms throughout the day, and in this coming CVPR. So what I'm going to tell you is going to be a little bit different, because as part of Amap and as part of the support for a huge business, we face a lot of challenges that we don't hear a lot normally, and we should have to take a systems approach and try to solve these challenges from many different points of view. So I will tell you about these challenges and about mapping and navigation in a hectic world. So let's get started. I think I want to very, very, very quickly tell you about Alibaba. If you are in China, of course, you know all about Alibaba. It's hard to avoid it. It's part of the life. But if you're outside China, you probably have heard about it in news, but you may not have a global view of what Alibaba is. I want to tell you a few things. First, Alibaba is based in Hangzhou. Hangzhou is arguably one of the most beautiful cities in China, and it also happens to be my hometown. So I highly recommend it when the pandemic goes away, and if you travel to China, please make sure that you have a chance to visit Hangzhou, because it's really beautiful there any time of the year. In terms of the Alibaba business, it's not just e-commerce, although e-commerce is the one thing that we hear about most. It's also has many different parts of the company working on things like digital entertainment, logistics, local services, and financial services. And Amap is part of this ecosystem. We are probably unique in a way that we serve a lot of customers on the front end based on the navigation app, but we also view ourselves as an infrastructure type of thing that we provide to the rest of the Alibaba group. So who's Amap? Amap is the #1 mapping and navigation company in China. And as of lately, we now have 100 million daily active users. So that's really a lot. So like every day we have 100 million people using Amap, using the navigation app, mostly on their phones. And even though our primary business is in China, it's still a huge problem. Like there are over 8 million kilometers of roads. In terms of POI, or so-called point of interest, there are over 70 millions. So in a way, Amap is really a big data company. And it's huge. So this is a list of the apps in China that, in terms of the market penetration rates, and for Amap, it's right there. It's like used by everybody, and almost 50% of the population use it on a monthly basis. So in terms of the big data, we really have a lot of data. On the one hand, we have the users. We have 100 million daily active users. We have a lot of data from the users. And on the other hand, we have the map itself, covering all parts of China with 8 million roads and 70 million point of interests. And one picture or one analogy we often make at the company is that it's like a person that has the upper body and lower body. And the map part is the lower body that really supports a lot of the user experience that we do on the upper body part. So this is what I want to talk about today, and it really covers several parts of the computer vision work that we do at Amap. There's a mapping part, and it's really try to use algorithms and automation to make mapping both efficient and accurate. And there are two parts, and one is we hear a lot about autonomous driving and the high definition maps that need to go with it. But there's also another part. Is what I call the standard map, or the regular map, is that for the 100 million daily active users, what they use, the map that's underlying the navigation app that people use, is also a big part of the problem, and that we also spent a fair amount of effort in solving and improving. And this is the mapping part, and also there's a navigation part, because the mapping is only the underlying data, and it needs to translate into user experience and how we help people navigate. So this is also something that I want to talk about. Okay, let's get started with the standard map, and so to tell you what we do in terms of that part of the problem. This is a very quick view of the pipeline for any mapping. There's a data acquisition part, and nowadays, just like everybody else, we use a lot of algorithms, a lot of deep learning, and everything else, try to do automatic recognition so that we can build and update map automatically. And there's a human element, because no matter what we do, algorithms always have their limits. So there is a part where human will provide their inputs to correct errors, or they handle the hardest parts of the mapping process. There's a fusion, and then it goes into a database and the service that can provide the map to the users. So this is all very standard. This is an example of what we do in terms of detection and recognition. So let's say we acquire the image on the road, and there are lots of signs on the road, and we need to understand what's on these signs and build those information into the map. So the standard pipeline will have a detection part to find the signs, with the classification part to classify them into all different types of signs, and there's a more detailed part of actually try to understand what's on each of the signs. For example, for a sign like that, it says it's not allowed for a long distance coach between the time of 2 o'clock and 5 o'clock in the morning. So these are the basic problems that we just need to solve. And of course, some of you would have this question, like, why is this still a problem? It seems like, after people have been working on this for some time, several years, it could have been solved, but it's not. It's still an ongoing effort. And one of the reasons is that mapping is actually a fairly deep business. There are a lot of things in it, and some of the things I actually didn't know until I joined the mapping and navigation company. So there's a lot of good that's going on under the cover, and as we all know, the real world can be fairly complicated. Driving in the desert by yourself is one thing. Putting a car on the road is something that's entirely different. And this is especially true in some of the fast developing parts of the world, especially like Asia and China. There's really a lot of growth and expansion, and things can get a bit hectic from time to time. So there are several challenges that we need to handle. One is obviously scale. And it's a big world. There are a lot of roads and signs and a lot of information that people actually need for driving and navigation. And with scale, it comes with diversity. And another challenge is the complexity of the map itself. Even the definition of a map, even the standard map that we use that supports a navigation app, it can actually be quite complex. Accuracy, obviously, people really care about the accuracy of maps and navigation. If we get it wrong one time, guaranteed there are people will be pissed off, and they will probably not stop using our app and try to switch to something else. And last but not the least, that we don't hear enough about is the cost part. And to handle something at such a scale, and the cost is really important. And we need to control it in every part of the pipeline, from data acquisition. So that's why we have a huge problem with data quality, and with the algorithms, and with humans, and all need to be considered in terms of cost. So we need both cost and quality. For example, the images that we work with every day is not something like this, but like that. It's really much more challenging that than people would normally realize if you haven't worked on this problem, or even haven't really taken into consideration cost as one of the first priorities. So these images are from very low cost devices. And there are a lot of issues in terms of distortion, reflection, occlusion, of course, naturally happens, but the resolution, the compression, the image quality, all of these actually impact our ability to understand and extract information from these images at scale. And small objects is obviously a problem. This is an example of something that may actually be unique in China. So in terms of mapping process, we also want to recognize and find those traffic surveillance cameras. They're part of the driving experience. So for something that's small, and for someone like me who've been in the field for a long time, what I like to do is a lot of times called, I think it's called pixel peeping, is that you actually zoom in. I'm sure everyone has this experience that when you zoom in, things really don't look the way they are, and there's not that much information in terms of finding small scale objects. And scene complexity is one big part. Now, if you live in the US, and you may have a mental image of a street scene like this, shops lined in a row with very nice, clear signs. But sometimes things can get really complicated. It's not like the thing that we see previously. It can be very crowded, and there can be a huge amount of information just from a single image. And there's also ambiguity. For example, as I mentioned, the point of interest, so we need to find these shops, like the name of these shops and what the categories of these shops. But there are also a lot of texts that we see on the streets that are not actually names of shops. So we need to actually differentiate them. There's some information that's not relevant to map and the navigation. And some of the information are temporary, transient in terms of time, and we need to figure those things out. And there are a lot of other types of ambiguities. So, for example, in terms of the high definition map that we need to do, there's often a confusion between poles and tree trunks. This is fairly interesting because we do need to differentiate them, because it depends on the time of the year. The leaves may go away, and things could look actually quite different. So there are some ambiguities there. And this is an example, the information that we need in terms of driving. I mean, there are some openings on the road. People can properly turn, sometimes even illegally, but people still do that. So we need to decide whether some of these places people can turn or not. And sometimes the difference can be fairly subtle depending on whether we see, one or two obstacles on that opening. This can be a turnable or non-turnable junction. And of course, things change. Now these are just time-lapse satellite images that I grabbed from the web, just to show the idea, things do change, and things change a lot on the ground, and it's much more than what we can see from the satellite, from the air. So we need to keep up that change. So I need to update that map frequently. And last but not the least, one of the biggest problems that we need to handle is location. And as you can imagine, location is a huge part of the mapping problem. And due to many reasons, even we have GPS today and it keeps improving, they're still problematic, especially if you have low-cost devices. So this is an example that I find, the red dots in there indicate the ground truth locations, and the yellow dots there indicate the actual GPS readings. So it can really be far from the actual location. I've had a personal experience that I've had issues like of errors up to 700 meters, especially if you just go out a building or a subway station, the location can really be messed up. So we need to find a solution to that, to build an accurate map in terms of inaccurate input GPS locations. So let me mention a couple of things just in terms of the actual algorithm that we're going to do to solving some of these challenges. So I mentioned these traffic surveillance cameras, we call it electronic eyes. Now think about the detection problem. We need to find such a small object in an image like this with a limited compute budget. How we solve these, as anyone who worked in the industry would know, data is the most important issue, and there's no way to get around it. There's always iterative development involved. We need to build a model, we test it, we find out what's not working, and and improved it accordingly. And there are some standard practices we do. We need a feedback loop, like when we get an error, maybe humans correct it, and the algorithms need to be adjusted in terms of these errors. And there's also needs to be the data mining part, because you want to focus both your training data and the labeling effort on the thing that's really challenging and that what you really need. And inevitably, there will be ambiguities in terms of the labels, and sometimes errors, because not all the classes are well defined, so that sometimes even humans would not know know what it is. So there are some techniques we can use to help mitigate that problem, like label smoothing, or begin to focal loss on multiple classes, either symmetric or asymmetric. There are other things we can do to help handling the labeling ambiguities. In terms of the seeing variability, we always have different type of seeings, and increasingly we are moving to semi-supervised learning because it's not really even though people have been working on that for a long time. I think this is this is a time that it actually starts to work. So we've been increasing using techniques in terms of semi-supervised learning to utilize the huge amount of unlabeled data or weakly labeled data that we have to help improve, for example, in terms of detection of these small objects. And of course, there are the issues of the small objects themselves. There are techniques we can do to help the accuracy of performance on the small scale end. And as I mentioned, the map needs to be updated all the time, which means that every time we go and collect data, most of the things in the scene actually doesn't change. For example, I show two examples of those cameras here. These are from two different collections, and they look quite different, but actually they are the same object. So once we figure out that they're the same object, then we don't need to process it again. So that saves a lot of both computation and human effort. So how do we know it's actually the same object? It needs to be done at multiple levels. There's an object level matching, based on the semantic information or the content of these objects. And there's a context level matching, for the things that around this object. And for this case, there are different ways that these cameras are mounted on the rail, and that helps with matching. And there's a scene level matching. We can take these two images, and we will match these two images to see how likely they come from the same scene. And this is roughly about location, and we can also try to handle the location problem explicitly and try to do structure of motion type of approach to improve the location and correct for the GPS. So in terms of this problem, intuitively, it's very natural. We have inaccurate GPS locations, we have images, and we can run structure of motion to find out, to get better locations. But in terms of practice, it's actually a huge challenge. One is, of course, scale. As I mentioned, there are 8 million kilometers of roads in China because the roads needs to be updated. And so there are multiple data collections on each road every year. So every year, in terms of the mileage of the data we collect, is over 30 million kilometers. And sometimes we also need to go back and fix locations for the older data. So overall, there's over 1 billion images. And this has to be done with low computational cost because this is only one part of the system. We cannot afford to use expensive algorithms to solve this problem. So unfortunately, many of the algorithm developments that we see in academia lately, for example, using deep learning techniques, they cannot directly apply to our problems. We have to find a different way. And data quality I already mentioned, it's also a huge problem if we want to, not only when we do recognition, but also when we do structure of motion type of geometry-based algorithms. We're working on it. It's still work in progress, but we can do it to a large extent. We can balance robustness with efficiency, and I can tell you that semantic information actually are key to this process, because geometric information may not be enough, and because we are already extracting semantic information from these images, so in a sense they come for free. Let me show you an example. So in these examples, the dots, the dark blue dots, are the original locations, and you can see that it's really off both in terms of translation and rotation. And so when we apply structure of motion or semantic structure of motion to it, we can actually fix those and make it much more accurate than before. And that really helps us in terms of the mapping process. Okay, so that's what I want to say about the standard maps. And now next I want to talk about the high definition maps. And you probably already heard about some of the related issues and approaches in the previous talks today. And since I think there's no argument that autonomous driving is the future. Usually the argument is when that future is. So we've also been spending a fair amount of effort on building the high definition maps. And arguably we are the leading high definition map builder and provider in China. And we really focus a lot of our efforts on accuracy. With the accuracy that we shoot for is, in terms of relative accuracy, 100 meters, 10 centimeters at 100 meters, which means that if there are two map elements that are 100 meters apart and their relative location accuracy is up to 10 centimeters. So that's really very accurate. And so we believe the accuracy is actually a huge part of this, the HD map. And as mentioned, cost is also part of it. Of course, the cost of building HD maps is very different from building the SD maps. But still, the cost is something that's on the top of our mind. And once we reach the accuracy goal, the most of our efforts goes into how we can actually lower them. And also there's a big part of it is how to keep the map fresh. So we need to update the HD maps, from yearly frequency to monthly to weekly, and so and I think this is actually very important and very essential that we have a fresh HD map that we can support the autonomous driving or the whatever level that it is to actually run safely and comfortably on the road. So there are three different problems that we work on in terms of building the HD map. So one is the data alignment. Is that that the data, especially the point cloud data that come in, we need to actually align them so that we can get an accurate map out as an output. The second part is more close to what I talked about. The SD map is that there is a huge recognition, or should I say semantic segmentation part to extract the map elements from the input, and in order to do automatic or semi-automatic HD map generation. And there's also an update part that I will also talk more about that later. So here's an example of the alignment problem. So this is an animation. The unaligned data is on the left, and the aligned data is on the right, and you can definitely see overlapping point clouds when they are not aligned. Even though in terms of the HD maps, we have fairly high-end data acquisition vehicles with very good GPS and processing. If you go through the same road twice, the location error can still be up to 1 meter, and which is way too much. And so we need to align them so that if we do different runs of data acquisition on a road, the accuracy will be up to 5 centimeters. So how do we solve this problem? Naturally, there are two parts. There's a local part. At each location, we try to align, and in this case, mostly just the point cloud. ICP is the standard technique, and that's been around for a long time. There's not that much improvement in terms of pure point cloud registration, but we do a lot of other things. One is the semantic part, is that to understand the semantic labels of the point cloud is really very helpful for us to do the alignment. And also increasingly we have been using a learning-based approach to go together with ICP or to replace ICP so that we can leverage more recent techniques to do the alignment more accurately, to handle some of the issues that we always know about in algorithm like ICP. So there are a number of ways we can do the local alignment and to make each local part line together. But there's also a global part because we cannot just shift data point clouds on one part of the road or just one road without impacting on the other roads. All the roads are connected together. So especially for a crowded city, oftentimes we really need to do optimization at a large scale. And the typical scale that we have to handle is can be up to 10,000 kilometers, and there can be more than 2 terabytes of data and millions of variables. So we can actually do that. We do a spline-based approach, and there are sparsity in the system that is non-trivial, but we can explore. So by doing large-scale sparse optimization, we can actually solve this problem within hours, which is very helpful in terms of solving this alignment problem at scale and in large cities. And so far I've mentioned the alignment problem, just assuming that each pass of the data collection, the trajectories are good, but that's actually not the case in many situations. We've done analysis, and in challenging areas, even though we have very good GPS and the GNSS systems, the accuracy of these source data may be as low as 60%. So if you're a mountainous area, or if you're in an urban canyon, and there are many places where even a very high-end GPS signal is not good enough in terms of HD maps. So the red places that I show in these pictures are the places where it's not good. And so we need to fix those. And running type of LiDAR-based SLAM algorithm is the most natural choice. But there are challenges, of course. One is in terms of the accuracy, and then two is also as we move away from the very high-end devices, for example, the LiDARs, the point cloud data quality can also become an issue. So again, just like I mentioned before, there are multiple ways we can solve the problem. We can use the original point clouds. We leverage geometric features like lines and planes and other things like corners. And we also heavily rely on nowadays on semantic features like pose and other things where we can actually fit a parametric model. So that really helps us to align these objects and then to align these point clouds as a result. And there's also an optimization component involved. I will not go into the details, but it's also non-trivial. There are several useful technical choices that we can make in terms of the fusion of the LiDAR data with MU and RTK GPS. So this is an example of the output. Originally, there can be alignment error, and after on a LiDAR SLAM algorithm, these errors can be corrected. And this is a quick comparison of our own data in terms of the accuracy. And so you can see that we can actually do a lot better than the open source algorithms that we can find nowadays. Partly because we actually do a lot of other things than pure point cloud alignment. Okay, so now let me move on to the map generation part. And the problem that we face is that we have input data, we have point cloud and images, and we need to output an high division map looking like this. And there are many elements in the map, from the signs to the guardrails and the markings, ground signs, curbstones. There are really a lot of these, and one main challenge that we need to have is that we need to have very high recall, and in terms of location accuracy. So it's a fairly challenging problem, challenging in a different way comparing to what I talked about for the SD maps. So we need to do both image and point cloud recognition or segmentation. And it should not be that surprising that we don't just do deep learning. There are traditional methods somewhere in these pipeline that it's also quite helpful. Part of the reason is that there are prior knowledge or regularity of the scenes that we need to build into this pipeline. It's much easier to do with traditional methods. And we also try our best to reuse our data and model from our SD maps. It helps, especially in the beginning when we have fairly limited data for training and testing. There are a couple of things I want to just quickly mention. For a long time, sort of obsessed with the issue of scale, and I think about scale as the most fundamental problem in computer vision. So we did a couple of things that's open source. One is how we can actually do multi-scale semantic segmentation. As you all know, the original encoder-decoder structure looked like this, and there have been many people working on that and the improvements on it. And I think we actually have a good solution now. This is one of the things that we did in terms of the what we think about as should be the best structure doing multi-scale fusion. Is looking like a pyramid like this. So there are the original encoder-decoder path. There are multiple lateral links, but in each stage in the lateral links, we can also do both downward and upward links. So these all these links and connections actually do help with feature fusion. So we did a number of tests, the standard cityscape data set. It's actually useful, and we've been using this type of techniques quite a bit. And this is useful, especially in a competition limited setting when we don't want to spend a huge amount of compute on just one image. And interestingly, the similar type of idea can also be made to work on point clouds. So this is just a quick example of what we find is that by doing this kind of pyramid-based feature fusion at multiple scales, we can actually have very large improvements over baselines, strong baselines such as kpconf, pkconf. So this type of multi-scale feature fusion is a part of the system that we're building to help handle the problem, because the scale does exhibit itself as a big issue in terms of everything that we do. Just some of the examples that interesting that we need to solve. One is the one what we call natural boundaries. So like the boundary between concrete and dirt, and sometimes it's really hard to see, and we need to actually find it accurately. And one is, this is one interesting, there's if you look carefully, there is actually a metal guardrail in there, but it's actually mostly occluded by the vegetation. And of course, come winter, this vegetation may go away. So we really need to find out what's in there. And I already mentioned there's a chronic confusion between poles and tree trunks that we have to solve. And for the lane markings, there's one big issue is that there could be aberrations on the road. So sometimes the signs are not very clear. Beyond a certain point, we will just say that this is a sign that we cannot reliably find and locate. But there's a huge gray area where we actually have to solve this problem, but the signal from both the point cloud and the image is not as strong as we would normally think. So this is just an example of the output. Is the sort of the HD maps that we have been outputting, and again this is doing it at scale. So in terms of the highways on the high grid roads in China, they're already down, and so we've been working on the large cities, and it's all coming. And as I mentioned that in my view, updating HD map is critical, because we can state the obvious that any map that is out of date is inaccurate. So if we want an accurate map, it has to be up to date. So there comes a number of considerations. If we need to do frequent updates, then this really need to be at low cost. So this pretty much rolls out the option of using dedicated vehicles to do this. Unless, of course, you don't care about the cost, then there's a different story. But if you care about the cost, it's very hard to do it with dedicated vehicles. And there's also a natural tendency. I think many people in the field would also make this choice, is that going to do a vision-only device. Of course, there are low-cost LiDAR devices coming out now, but both in terms of the maturity and in terms of the quality of the point cloud, that's still hard to say for sure. So most of our efforts are still focused on vision-only devices. So we build a small device. And it only has a camera, it doesn't have a LiDAR. And we want to see if we can actually use it to update HD maps. Now the question first is accuracy, especially in terms of location accuracy. Is it possible to actually get to 10 centimeter accuracy with a vision-only device? And I'm very happy to say that it's actually doable. So this is an example of the type of video that we capture with this vision-only device. What's shown here is the overlay of an existing HD map on the actual video. So what you can see here is that the HD map, the red and green lines and the signs, the boundary of the signs actually align quite well with the actual scene. So this just shows that it's actually feasible to do very high accuracy relocalization on the vision-only device. And of course, the relocalization is a complicated problem that has several components. Now, there is another problem that we also need to solve, is that even if we go with vision-only devices, if we have to support and deploy a large number of these devices, it can still be expensive. So how do we solve that problem? The solution that we find is this. We want to use existing ultra low cost devices for change detection. So remember what I told you about our SD maps. We have lots of devices already running on the road that they are very low cost, very low quality, but they are there. And we can use these to do so-called change detection. So if something changes in the physical environment, in the real world, let's say there's a new sign being added, and we want to use these existing devices to find the change. And these devices, the image or the data from those devices, not enough to do HD map update, but they are more or less good enough for change detection. So once we find the change, so we can actually get one of these our better or slightly better devices to get more high quality data and use it to update the HD map. So this is the process that we believe will actually make it feasible finally to actually do high frequency update of the HD maps. And there are a number of technical challenges, of course. There's a bandwidth issue and there's a compute issue. This is really low-end devices, so there's a very limited amount of compute and memory that we can use on these devices. In addition to the issues that I mentioned when I talk about SD maps, is in terms of image quality and poor localization. So this is going on. Again, this is not just a study. We are actually we're rolling this out as we speak, and I want to show you one example of the things that we need to do. And obviously, we need to do recognition part. There needs to be both semantic segmentation and object detection on the device. We spent quite a bit of time optimizing these small models, and in terms of accuracy, it's reasonably high, and both qualitatively you can see from the video and quantitatively from the numbers. It's not as good as like a big model, but it's a feasible problem. Okay, so this is what I want to talk about the mapping part, both in terms of the SD maps and the HD maps. Now I want to shift the gear a little and talk about navigation. The map by itself is not particularly useful. There has to be navigation, and ideally there should be a synergy between maps and navigations. And we've been working on this for some time. Is that we want to find out how we can actually do navigation better, how we can actually be more intuitive and be more useful to the end users. And let me mention one example from a personal experience. This is, of course, before the pandemic, and we took a vacation in Spain, and there are a lot of roundabouts in Spain, a lot more than in the US. So in Spain, I use use Google Maps. Amap is not available, and it often gives me instructions like take the third exit of the roundabout. And even though I think myself as reasonably good at orientation and navigation, I did make a few mistakes, because sometimes it's really hard to know whether one opening is an exit or is not an exit. So I counted it wrong. I'm sure many of you also have the experience that navigation is not ideal. We do make mistakes as end users, and sometimes can even go a little bit crazy. For this is an example of a junction in Beijing, and if you come from the west and you want to turn to south here, there are two possible ways. At midnight you can follow the red line and just do a 90-degree turn, but during the day there is actually you have to follow the yellow line, and even though I mentioned this a few times, I don't even know how many degrees there are. It's probably 810 degrees. So you need to make a lot of turns to actually get on the to turn at that junction. And arguably, there's actually a sign to tell you what to do. But I'm sure you can imagine, you know, how confusing it may be for someone who's never been there to see a sign like this. So what we want to do is that, you know, we want to think about, you know, we want to work on the next generation user experience for navigation. We want to find a better way. And obviously there are a number of components in there. And, you know, there's a map part and there's a location part. And there's also in terms of directions that we get from the navigation apps that we want to make it more intuitive. So one of the attempts is what you see is what you get. So in terms of map, you know, normally what you see on a navigation app in terms of map is something on the left, a standard top-down 2D view, or to actually make it better is that when you get to some of the junctions, you have a pseudo 3D view of the scene. But it would be much better if you can actually have something that, you know, directly tell you how to drive and what is the way to go. So that's something we've been working on for a while. And the first version of this we launched more than 2 years ago. So this is a something we call AR navigation, is that we want to leverage the AR type of visualization to help people navigate. And the example of video is like this. So when you drive, there are many ways we can visualize information in AR. This is trying to keep in the road, on the lane, on the road. And this is a warning for getting on the divider. When you get to a turn, it will give you multiple there's another arrow there. So a bit like what you might see in a video game, is that there are big arrows that actually tell you to turn. And this is in an entering a highway. So tell you should make a turn on the left. And when you get closer, there's actually a line that tell you exactly where to go. And I find this is actually very intuitive and useful. And in this system, we're also building some very lightweight assisted driving type of things, like warning of the vehicles if they get too close. And there are other things as well. For example, you know, traffic like speed limit and traffic lights and other type of things. So let me show you a more recent example. This is actually a complicated situation where you need to make multiple lane changes to get on the highway. This is again about warning of the cars, where we have cars and pedestrians, and we also made it work at night. We didn't have this at launch, but now we actually can do fairly reasonably well at night. So these are all interesting, and you might wonder, you know, like this is something that you may have seen quite a few times already. This is nothing surprising, but there's something that's very different in terms of what we do. Is that we actually have a very low cost approach. We actually want this to be available to people like today, not five years from today. So in terms of sensing, you know, instead of very complicated suite of sensors, we just have one camera, and that's typically not high-end camera either. And more importantly, in terms of compute, we also want this just to run on a low-end ARM device, ARM CPU. So this is really like magnitudes different from what you normally see in autonomous driving cars. So you just imagine it's only about a fifth of the compute power as your smartphone. And we have to do all of these things. And how do we do that? There are a number of things we need to do. First, we need to do a multitasking model. We cannot do multiple models. We need to do compression in terms of many different types of approaches. The implementation itself is also need to be optimized, and there are also system level optimizations we need to make it work. But it actually works. So I'm very happy that this is now running on very low-end devices and adopted by a large number of users already. And of course, you know, AR may not be for everyone, especially we still don't have HUD displays on most of the cars. So this on a phone or another screen may be mentally overloading. But the same type of thing, we don't have to do it on using AI type of visualization. We can actually do it in a more abstract way of visualization. So this is something we also recently launched. We call it lane level navigation. This is you can already do it on the Amap phones and also on a number of cars that are just coming out in China. And from all that I can hear, everyone that used it actually find it much better than the normal road-based navigation, because this can be much more accurate in terms of the direction that it gives you. So this is actually quite, I think it's quite exciting. And there's a vision. There's a camera-based version of this that we do vision-based localization to do both the lateral localization to decide which lane we are on, and to do the localization along the road to know how far we are from the junctions, and et cetera. So the vision-based localization is a really big part of the system of the lane-based navigation. Okay, so I think that's most that I want to mention is that there are a lot of computation work going on at Amap. We face a lot of real world challenges. There's a huge part is mapping and mapping automation for both SD maps and HD maps, but there's also a navigation part that I find it actually quite interesting. It's not a solved problem. We may not know the right answer, but I feel that it's actually something that we should pay more attention to. Because normally, especially at CVPR, the only thing we hear about is autonomous driving and self-driving cars. But for the foreseeable future, there's still be human drivers, and more often than not, the cars on the road are still driven by humans. So how we can actually make that better in terms of map, in terms of navigation, and in terms of how these two types of fishes can live together. I think these are all very interesting problems, and that have very interesting technical components in them. So this is a slogan that we have at Amap. It means connect to the real world and make travel better. And since we still have a little bit of time, I want to mention one thing in terms of my personal experience, is that when we think about computer vision applications, there are typically two types of things. One is in the real world, and one is in the virtual world, or what we could say that is on the cloud. And for quite some time, 10, 20 years ago, the only thing that we think about in terms of application, there are two things. On the cloud side, we think about the Google image search, and on the real world side, we think about surveillance. These are the two dominating type of real world application scenarios that we have in mind, and that preoccupied us for a long time. And of course, nowadays we have a lot more applications, both on the virtual world side and on the real world side, in terms of for example, like the Amazon Go store that I worked on for quite a few years on the real world side. And there's also some interesting applications that go across the boundary. Like, for example, one of the things I worked on at Alibaba is visual search, is that you take a picture of an object in the real world and you find it in the virtual store. So these are all very interesting problems. And in my personal view, is actually the thing, things that happen in the real world is much more exciting and challenging. Not just because the real world is complex, but also because there are fewer ways we can actually get information about the real world. In the virtual world, there are a lot of information we can use, like user clicks and other things. But in terms of things in the real world, vision is really a very promising way of trying to get all the information that we need, and has many advantages over competing type of techniques like the Internet of Things type of devices. And that's part of the reason that I chose to work on maps. It's exciting, and it also has a big impact in terms of real world applications. Like I mentioned, Amap today has 100 million users every day. And when I joined maybe more than 2 years ago, I think that number is much lower. It's probably at 60 million. So even though we are already a number one, we're still growing very fast. And there's a lot of innovations, including technical innovations that happen at Amap and I'm sure at other mapping and navigation companies as well. So I hope you'll find this interesting. Thank you.
Thank you, Xiaofeng. That was
Thank
a
you.
very good presentation, and especially sharing your personal experience on the application of the computer vision. So we do have two questions online. So let's first answer them, and then we'll open to the audience. The first question from Oleg is asking, is there a standard global coordinate system commonly used in mapping?
Yes, there is. There are lots of standards in terms of maps, and there are regulations as well. So I'm not an expert on that, but people have been doing maps even before the days of digital maps. So there are standards.
Okay. The next question is, how is an update triggered from the change detection? So that the change detection module you mentioned, and also related to that is, how is the confidence of that updates determined?
Just the usual way. And obviously, when we do something like change detection, recall is the primary objective. Precision is not necessarily that critical for a number of reasons. One is that once we actually transfer the images back, we can actually do another iteration of algorithm processing to use bigger and more sophisticated models to actually get the precision up. And as other parts of the system that I talked about, there is and there can be a human component as well. So if there are things that we're not sure, we just let human decide. So we don't have to be 100% autonomous. We can choose to where we want to be autonomous, but it's not necessarily required. And in terms of confidence, this is a perennial issue. Like we always have this issue, how to compute confidence. And this is, obviously there have been great works at CVPR and other places that can look at it from each individual algorithm's point of view. But in the end, just like most of the other things I talked about, is usually a fusion of information from multiple sources, and there is typically some kind of deep learning based modeling at the beginning, and then there's a machine learning component that does the fusion of multiple sources, and in the end we just have to validate it with real world data to see how good it is.
Okay, thanks. The next question is from Angela, asking, what is the database to store a map data?
So as I mentioned, that there are standards in terms of the format. And because Amap has been working on that quite well, and Amap actually existed before it joined with Alibaba, so it has its own system. It has its own system and the database, but we've been moving to the standard databases on the Alibaba cloud. So you think about the underlying database is a cloud database, and but in terms of the format and the organization, it really goes down to what I mentioned, where the map is a deep business. I don't know much about it, and I don't think you might find it boring if I actually do go into detail like that.
No problem. Last question online is, can you elaborate? Oh, another one. So can you elaborate more on how semantics are used for the structure for motion?
Yes. So there are a number of ways. One is that, in terms of recognition, we already have, and we do we recognize it, and so we know it's there, right? So this can be used together with the local feature-based structure for motion, and there are a number of ways you can do that. One is it already helps with feature matching inside the signs, because if you know it's the same sign, then you can just match the features inside those. And two is that the shape of these signs themselves can also be used in the boundary adjustment. So you can optimize together, and there are other information that you can use in terms of the geometry. For example, most of the signs are planar, and for pose, you can model it as a straight line or model it as a cylinder. Depends on how complex you want it to be. But these are the ways that semantic information can be used, and it's actually really helpful.
Thank you. And we have another question from Ying, whose question is, in the HD map production process, do you think it is possible to be fully automated? How far can it go?
Depends on the accuracy that you want. Now there are companies that do it or try to do it in the automatic way. Booij is a prominent example. Depends, very highly accurate, then I think it's still hard to do today or in the near future. If you want to do it automatic, sure, but there are things you need to sacrifice, both in terms of accuracy, the precision recall of your map, or the location accuracy of your map.
Okay, thank you. And I think that answers all the questions from online, so we can open up question for the audience. Feel free to unmute yourself and then ask questions or raise your hand. Okay, that's great. So we don't have more questions for this session. So this actually was the last speaker we have today, and thanks, Xiaofeng. I would like to also use other speakers, if you're still available now, that we can answer questions for the audience, or whoever is not, still have questions for other speakers. For example, Peter, I see Peter's there, but maybe too late for him. Oh, hey, you're still there. Olaf, and I don't know if other speakers are there, but just in general, I really appreciate all the speakers talk today. It's a full day, but I really appreciate everyone, especially the ones in Europe. You guys are already very late, and then really appreciate everyone's presentation today. And we'd like to also open the last questions, or a few questions for the audience, whoever still have questions for our speakers. Yes, that's a very interesting question. Ben is not able to make it today, and he actually shared with me a link for the video. However, the video cannot be played at this moment. So I will try to include that into the website we have. So even though he was not able to present today, I will try to include that for our, at least he prepared for this, and we know there are some technical challenges for him. So I'll later get that video and share it on our website, so that at least people will be able to review it offline. Any other questions from the audience? Okay, I have one question I want to ask everyone. So we're all working on maps, right? Including myself, used to work in here technology. So one challenge, at least what I see, and also this is a challenge for all the mapping company or whoever doing the actual map, is it seems like there's a lot of integrated solutions from the industry. And for example, you know, Waymo or Tesla, it seems like they don't need an external source for their mapping function, but they do want to have a mapping function within their unit. And then that's how they can make a very fast iteration on their map creation. So that seems to be a challenge for at least what I see from here or TomTom or other kind of specific mapping company perspective. Maybe Xiaofeng can also share that. So how do you view this? Like, do we, in the future, you know, not now, but in the future, do we need a specific company who's still like being specialized, providing maps for all the companies? Or the trend is becoming, you know, it's more like a Apple, like sort of a integrated company, and they will just do everything inside their group. What do you think? Or maybe this both trends will be continue going. Some company like to use external vendors, some company like to do their own mapping.
Yeah, so maybe I can start to answer what I think about this. So maybe this is also a bit about how TomTom is usually doing it traditionally, because they are traditionally very much working with trying to work with a lot of companies. So they have always been, because they started creating this navigation devices, right? Separate, but then the navigation devices got integrated into the cars quite quickly. Of course, like first when you have navigation devices, they have to be separate because it takes like 10 years for such developments to be in cars, like sold and on the road. But that already happened, and then it was like, and then they started by building their own devices, right? And TomTom just providing the services. And so for TomTom, it's really natural to be in this place where you just just have a lot of interaction with other companies and actually share a lot. So to have like also different relationship with different companies. Something a bit different than I think how some other companies like Google and this kind of more newer players in the field, maybe not newer. Yeah. If this will be the future, I don't know. But seeing that there's a lot of automotive companies, it's not like there's no monopoly, there's no like two players, no, there's a lot. I think this diversity will always be there because those companies also really like to not choose for one solution. They do not want to really be hooked up. You can see this with a lot of automotive companies. They always want this option to switch, and they sometimes do after some years having here maps in other systems, and then they go to TomTom or vice versa, or maybe Samsung or Google. So
that makes sense. Thank you for sharing.
But who knows? I wonder what the other people think.
Okay, let me add a few thoughts. I'm not too worried about that, you know, because the map it's actually takes a lot of efforts and investment to build maps. If you think about like the regular maps, Apple did, you know, spend the effort to build the maps, but it costed them a lot. So I don't think it's really necessary for each car company to build their own maps, and it will not be particularly efficient, and it will not actually make the most business sense. And there are a number of there are also other considerations that we could think about the problem. One is that there's always going to be there's an HD component, as I mentioned. You know, there's also an SD component. Like the normal maps that we use today, it's not going to become obsolete, because whenever you drive or navigate or plan for the routes, you have to have that layer of representation as well. So in the future, the map is not just an accurate representation of the real world where you use it for localization. There are other ways that map is also critical. So I would also imagine that also an argument saying that these companies may not want to just all do it for themselves. And a more practical argument, of course, is that today or in the near future, I'm sure that the mapping companies can do a lot better than these car companies. So once there are reliable maps available commercially on the market, there will be less incentive for the car companies to develop their own maps. And so part of it may just be a marketing type of thing. Some of the players may not be that serious about building their own maps. They just feel that they could do it, and that adds to the company's portfolio. It's just a few of my thoughts.
Thank you, Xiaofeng.
Yeah, maybe if I can also add something to this. So I would definitely agree with what the previous speakers said, in particular in terms of what the costs and the investment mean for companies. I mean, this is a huge amount of budget that has to be dedicated to keep maps up to date, to really keep them in a form and in a shape that it's helpful for the downstream product that people want to use it for. But maybe in broadening up a little bit more towards the general map availability, not just for the case of self-driving. I mean, a lot of companies are investing significant means to support OpenStreetMap initiatives and build more and more on these type of engagements. And I think the type of map data that comes from OpenStreetMap has been significantly increasing in the past years. The map data is very broad, is very generic for a much broader set of downstream applications. And that's also why I think that so many companies are trying to leverage on top of OpenStreetMap and support this effort. And I mean, eventually, this was also one of the first reasons why a few years back, Mapillary was founded, because there was this general idea of maps should be kind of publicly accessible, that silos should be broken up where data is being hosted and not accessible for many others. And now with Facebook, this hasn't actually changed. So Facebook is a strong supporter of the Mapillary spirit. People who are using the platform, they will not notice that we are changing our path here. So I think there's a lot of strong commitments from many different companies to really push also this sector of OpenStreetMap data.
Thank you all for sharing. I think the reason we're all here because this is a challenging problem. It's not going to be an easy problem to solve. So my second question, I think that's the last question I have, is we've shown a lot of good progress, right, using computer vision to solve the mapping problem. So I'd like each of you to share your thoughts on two things. One is what problem we have solved now, and the second question is what problem is still remaining for us, so that we can inspire more researchers or even from the audience who are interested to devote their time into this domain. Peter, since you're here, you can start.
Yes. The problem that we've solved, I think we've made a very good kind of progress in the context of object recognition, especially in recognition of everything that's relevant, for example, for the type of map making that we used to do at Mapillary. And that's really due to the big interest in the community of pushing this field forward, since there's so many applications, not just, of course, the ones that we see in the mapping community. I don't still think that we have solved this problem yet. So there's still a couple of very challenging things that need to be dealt with here. But I think on the more broader kind of side of problems that we should solve is the way how we leverage modern machine learning technology for the actual 3D modeling part, and make this go stronger together with semantic recognition to have better kind of and more abstract representations that are kind of machine digestible, that can be used in higher level kind of analyses. So something that departs a little bit from this conventional image-based 3D modeling techniques, and then there's this kind of parallel stream that tries to feed recognition information. I would like to see more work done in that field, and in fact, there's a couple of interesting branches that have been popping up in the last few, let's say, months and years. So I'm excited to see more of that.
Thank you, Peter. Xiaofeng, do you like to share some?
Yeah, as I mentioned in the talk, I don't think anything's solved. Especially, I keep mentioning the cost part. So I think in terms of how to efficiently do a lot of things, I think it's still fairly open. I'm not sure. I would agree that we've made huge progress in terms of recognition, like detection, classification, and the segmentation, and probably not so much in terms of 3D. But for all these problems, how can we actually have lower cost solutions would be a key, I think, for any large scale application.
Great. Olaf?
Oh, sorry. Yeah, you said Olaf, and I didn't recognize my name. Yeah, so my presentation was all about this, right? Like what I see as the biggest challenges ahead, which is like this. Yeah, maybe people can see this more like updating the map, keeping the map up to date, right? That the map is kind of a model, and how to keep on modeling it, right? You have some information already, now you get some new information, how to kind of fuse this in. Apart from also something I said about like treating the data more raw than what we do now. So removing some of the handcrafted stuff in the beginning. But maybe what I didn't mention, what I also think is a big topic, and it also came forward kind of in the talks that were now. There seems to be kind of this split kind of thinking about, well, some call it like SD and HD. So there's more like navigation or routing kind of map, which is topological, and this more high definition map, which is more like globally geometric consistent and these kind of things. I think it's quite an interesting topic. If you look in robotics, I think in the history, a lot of things were very topologic until like the 90s, when really this simultaneously localization and mapping was like solved, right? It seemed to be solved, and you could see it like really in practice in the beginning 2000s, right? So there's this real-time mono-SLAM and these kind of things. And now it seems like, okay, SLAM is really this thing that is about geometry, and HD is about geometry, and that's the thing you need to use. I think we should go back a bit on this, backtrack a bit on this, and see how you can make maps that are both like maybe topologically global, but locally geometric, so that you are relatively very good, you know where you are, but topologically you do not really, so globally you do not really need this geometric consistency. That's also where I see kind of a spot where it would be good to really like invest some time in investigating what kind of types of topological geometrical mapping can be how two worlds can be.
Thank you. I think there's some issue with my network. So I see some lagging on your last sentence, but appreciate your input. And I also appreciate everyone to stay this late for today's presentation. And this is the third time we get together to talk about mapping and how we use computer vision for mapping. I'm looking forward to maybe next year again that we can meet in person and we can talk more about how we can expand this community and also use computer vision to solve the practical problem that Xiaofeng has mentioned, or real world problem Xiaofeng has mentioned. I think all of us are actually interested in solving those real world problems. So I really appreciate everyone for your time, especially our speakers. Behind the scene, our speakers have spent plenty of time to prepare for the talks and also get through this challenging or presenting through internet. And I hope that in the upcoming year, we can meet together in person and we don't have to prepare this so way ahead of time and recording and then figuring out the timing. I know timing is another issue. You don't want to pass your time. So there's a lot of things going on behind the scenes. Thank you very much for everyone.
Thank you.
Thank you also, Sean, for organizing. Again, great stuff.
Okay, I think that concludes our tutorial today, and hope everyone who stayed with us enjoyed the tutorial. We will finish the recording today and share the recording through our website, Vision-Meets-Mapping.github.io, and also we'll share with the general community. Maybe there's a computer vision community website that we can share as well. Thank you, everyone. Have a good day.
Thanks.
Thanks, Xiang.
Bye.